Yes, you can proceed.
Okay, thank you, sir. Good afternoon, all, and welcome to the afternoon session of iSmart Conference 2021. To start with, we have a keynote lecture on automated product and process discovery of novel materials in the age of AI and robotic animation by Professor Harris Magatsaurus. Dr. Harris Magatsaurus is a professor of Sustainable Manufacturing Systems. A chartered engineer, he graduated from Imperial College London with a mechanical engineering degree and a PhD in manufacturing systems. And since he has spent 20 years in both industry and academia, devising and managing integrated development of research projects. His work combines mechanical engineering science with process system engineering and intelligent automation to accelerate the discovery, development, and sustainable manufacture of high-value chemicals. As a result, his research program combines both experimental and computational components. At the core of his work is process intensification techniques with emphasis on chemical reactor technology, and it is combined with algorithm-based automation. He has extensive expertise in process engineering, manufacturing systems, operations and control, and has been developing AI-controlled flow reactor systems for functional materials production for the last 10 years. Over to you, Dr. Harris.
Okay, thanks very much, everybody. I'll try to share my screen if I can. Let's see how this is going to work. Okay, this is one of the platforms we're not using at the university, so it is a little bit. I'm not so sure. What can you probably you can't see anything at the moment. Let me just. Can you see my screen?
Yes,
Yeah,
sir.
it's visible.
All right. Okay. So can you see my screen now?
Yeah, it is. We can see it.
So you see my first slide?
Yeah, I do.
Excellent. Okay. Well, thanks very much, and thanks very much for inviting me to
Professor Harris, sir, we are facing a technical issue from your side. Can you please check that? Participants, please wait. We'll resume the session soon while he rejoins the session. Good afternoon, Professor Sunil sir.
Hello.
Sunil sir, are you ready for the presentation?
Yeah, it is ready.
Okay, sir. We'll give a brief introduction. Gokul.
Okay.
Yes, sir. So
We
moving
can
on to the next.
we can move on to the second session by
Okay.
Dr. Sunil Pathak.
Okay. So next we have a keynote lecture by Dr. Sunil Pathak on the topic laser shock peening and its benefits in real world. Dr. Sunil Pathak was awarded his PhD in mechanical engineering from Indian Institute of Technology. He is currently a senior researcher at Haile Center, Institute of Physics, and Czech Academy of Sciences. He specialized in gear engineering and advanced hybrid manufacturing processes. He has been working in the field of gear engineering since the last 10 years and advanced manufacturing for over 8 years. Dr. Sonal has authored more than 25 research articles, one monograph, two edited books, and more than 15 manuscripts published as book chapters in various international conferences. Dr. Sunil Pathak, I might invite you to take over.
Yeah. Thank you. Is it hello to everyone?
Yes, sir.
Uh,
You're audible, sir.
I'm audible. My presentation is visible.
Yes, your
Yes.
presentation also visible, sir.
Okay. Can I make it full screen? Just a minute.
Okay, sir.
Okay.
So, good afternoon to everyone, and I hope all of you are safe and healthy in this current scenario. So, I will be presenting a seminar on this laser shock peening for the real world. As described in my introduction, I'm Sunil Pathak. I'm working as a senior researcher at Hiless Center. So I will be giving, this is the agenda of the talk, like a brief highlight on the Hiless, what is Hiless, what Hiless is doing, and then introduction to the laser shock peening, then LSP application and future work at the Hiless. So basically, Hiless is a mix of two words, high and laser. So it becomes a Hiless. Hiless is a part of Institute of Physics, Czech Academy of Sciences. It is a R&D center providing diode pumped solid state lasers with breakthrough parameters. It is started in 2016 and running well. So it is one of the national interest project of Czech government. The financial year 2000 year budget was around 4 million euros, and the main thing is like it is 14% only institutional and 86% was from the projects. And basically what we are doing laser development plus then theory of laser matter interaction, including experiments in optics, photonics, and nanomaterials, and thus serving the super lasers for the real world. Now, I will move to the introduction to the laser shock peening. As we all know, laser shock peening is a cold working process that plastically deforms the material, imparting deep compressive residual stresses. As you can see in this figure, like it works basically on the four principles. The first one is delivery of the laser beam with a defined energy, delivery of the laser beam to the workpiece at a defined energy, plasma generation on the surface of the material under a confined medium, and then propagation of the high shock waves in the material, which can be seen here, and plastic deformation and generation of the residual stresses inside the material. So basically, we are developing the compressive residual stresses so that the material will become high strength and less reactive to the fatigue. What are the benefits of laser shock peening? Is like fatigue enhancement in the fatigue life, stress corrosion cracking resistance improvement, wear resistance improvement, preventing high cost failures, less downtime of machinery, longer time between the part replacement, improved safety, lasting of the pinning is almost equivalent to the lasting of the pin structure. And what are the commonly used materials are aluminum alloy, structural and alloy steels, titanium alloy, nickel alloy, and the major application belongs to aerospace, nuclear, power generation, maritime, additive manufacturing, tooling, and maintenance services. In the next slide, I will present some comparison, a short comparison of short pinning and laser shock pinning. How shock pinning, laser shock pinning is beneficial over the short pinning process. So the well-established short pinning is used on all rotating components on the entire surface in order to negate the tensile stresses induced by the normal machining operations. The short pinning process is generally cause severe surface damage, high roughnesses, and large amount of cold work. As a consequence, the material becomes quite unstable, and most of the process induced compressive stresses are lost quickly at a elevated temperature. So as you can see in this figure, like laser pinning can develop deeper compressive stress up to 2 mm, whereas the short pinning is able to develop stresses up to 0.5 mm. Means higher depth can be achieved by LSP, laser shock pinning. Higher precision, then roughness. Roughness is low in case of laser shock pinning, while more crater and more surface damage is being created in the short pinning. Fatigue life has been improved by 10 times more as compared to the short pinning because of the deeper residual stresses, as you can see in this figure, residual stress profile comparison. This is the machine. The green one is the machine, simple machine of titanium alloy, and then red one is the short pin, and this black line is for the titanium alloy laser treatment after laser shock pinning treatment. We can see the deeper compressive stress has been developed in the case of laser shock pinning, thus longer lifetime of the component. Now I will brief you a little about the what we have at the highlights. So we have a high intensity nanosecond laser systems which is having a square top hat laser beam profile. It is continuous process program. We are doing the continuous process parameter monitoring. We have a robotic arm for easy component manipulation and processing of complicated geometry parts. Robotic precision is 10 microns. It is having a load capacity of 20 kg, which will be soon increased to 50 kg. It is a fully automated process. Characterization equipment, we have the sample cell preparation system, everything, which you can see in the images. Like this is the LSP cell, then hole drilling device, X-ray diffraction device, and sample preparation cell. Now I will be moving towards the compressive residual stress and fatigue strength. So cracks either pre-exist or macro cracks initialize at high stress intensity regions. These cracks grows due to fatigue tensile loading, and our purpose is to mitigate this tensile stress and develop compressive stresses in the material to overcome this type of cracks and these things like failures. LSP induces compressive residual stress to protect the material from fatigue, crack failure, or slow crack propagation rates greatly by negating the applied tensile stress. That is what I have told you. LSP-induced compressive residual stress can significantly increase the fatigue life by 2 to 5 times. As you can see here, this is the control group to like having the life cycle of less than 1 million. Then here we are having, if we are pinning by the, this for aluminum alloy, if we are pinning by laser, it is giving the life cycle of more than 1 million fatigue cycles. Now I will be moving towards application of the LSP. So first application, we will see something in the aerospace. The typical problems are fatigue life improvement, which is demand from the aerospace industries, foreign object damage resistance, resistance to stress corrosion, cracking, And what are the typical materials used for the aerospace is aluminum alloy 7075 or 6065, titanium alloy Ti6A, Al4V, and then Inconel alloy, Inconel 718 or 600, and AISI steels. So here you can see in 1990, the B-1 Lancer bomber was facing the problem of foreign object damage. The defect on the blades serves as a seed to fatigue cracks. The blades was damaged, was creating small cracks of fatigue, and because of this, the foreign object damage was increasing. And there is a one more example of the nuclear reactor in which corrosion cracking of vessel in the reactor that can be avoided by doing the laser shock pinning underwater and green laser delivered by optical fiber. Now what, like how to solve this problem is like the major benefit of LSP which I have observed is clear and clever definition of the problem. Treatment of just on the critical areas where the failure or the more fatigue failure are occurring. Redistribution stress by the LSP. LSP is in part in the stress is in the part is in equilibrium. You can see like here the cracks to failures here and here. So we have to do LSP here. We can do LSP here and make the stresses is in equilibrium and redistribute the stress which is possible by LSP and not possible by any other processes. Now another example in the power generation industry is the land-based gas and steam generator blades, which can be seen here. These are used and these are heavily affected due to stress corrosion, which are very minute corrosion type of stress type of corrosion which is occurred due to stress. Then there is a small video I want to show you. You can see how we are working on the laser shock pinning. This is the LSP processing for the pump blades. So we can see by improving the compressive residual stresses, we can avoid the minor cracks which are generating the corrosion also in the blades. And now this is the example of fatigue life improvement of nuclear reactor steel, austenitic steel type this mentioned here. Like this is the unpinned and this is the pinned LSP. We can see high corrosion resistance, problem with the stress corrosion due to these are the problems which the material is suffering. High corrosion resistance and then problem with stress corrosion cracking due to material sensitization. Compressive stresses induced by LSP pinning eliminate tensile stresses necessary for the stress corrosion cracking, and we will be discussing about the stress corrosion cracking a little more in detail in the next slides. So here now the stress corrosion cracking, like it is an environmental induced cracking, catastrophic from a corrosion, fine cracks, hard to detect and damage, hard to predict, often progress rapidly. Only tensile stresses are needed. Prevention by eliminating one of the three necessary conditions. What are the three necessary conditions is like corrosion, stress corrosion cracking, and tensile stresses. Then by including the LSP, by implementing the LSP, we are able to mitigate these two stress corrosion cracking and tensile stresses. Means not almost everything we can improve, but at least we can improve the two major things, that is stress corrosion cracking and tensile stresses. Thus the life of the part will be increased. Now these are the potential applications of uh, LSP in heavy industrial things, like these gears and camshafts. These are basically fun going under through the cyclic loading, and failure are occurring due to fatigue. So if you are able to do the LSP, these problems can be avoided. And the typical examples of this are trucks, mining, earth moving equipments, pumps, transmission gears, axle crankshaft, engine parts, impellers. And now I can say like potential application in the medical field, like orthopedic implants, hip joints, knee joints, spinal roots, fixation devices. And one more area which is not mentioned here is the dental implants. So dental implants, we are using titanium, and like it is having a life cycle of 5 to 8 years. But by improving the strength, by improving the um, its residual inside residual stresses, the life cycle of this can be increased. In the similar way, we can use it for the like, as you all know, maybe the titanium alloy are the most commonly used material for all these implants. So if the more deeper residual stresses are there, we can have longer service life, better life cycle, and lower fatigue failures. Now I will show you one more slide, which is like LSP in combination with the laser hardening. Means what, we are improving the residual stresses, and at the same time we are also improving the hardening. We are doing the hardness. So you can see here, this is the as received material, turbine blade, tool steel material, and this is what we have achieved after laser hardening of around minus 200 megapascals. And this is what we have achieved after LSP, alone LSP, somewhere around minus 800 to minus 900 megapascals. And this is what we have achieved after having the combined laser hardening and laser shock peening. It means deeper and more sustainable things can be achieved by hybridizing these two processes. So in the conclusions, I will say deeper residual stresses can be developed by using the laser shock peening as compared to the normal short peening process. Better quality of surface with less or no cost after treatment process can be achieved by laser shock peening. It is more flexible, variable parameter, not sensitive to angle of inclination. Means since it is we are passing the beam, it can go to into the intricate shapes like gears, profiles, and everything can be peened, which is not possible in case of the short pinning. And clean and eco-friendly, no material to take off, water you can reuse. Price and speed. So machines are expensive, but cost of diode laser is reducing over the last years, and treatment of small areas is very effective. Now I will show you what are the next future projects at the Highlands. We will be doing aluminum additive manufacture produced parts, fatigue life improvement, biomedical implants processing, hydrogen embrittlement resistance improvement, traditionally produced and AM produced parts, and fatigue life improvement for miniature and meso components. So you can contact me if you have any doubts, or if you want to connect, if you want to these things, and you can follow me on the LinkedIn. Hello.
Yes, sir, we can hear you.
Yeah. So
So,
since it was only for 20 minutes, I prepared something in this way.
thank you, sir. Thank you for this wonderful paperwork presentation. Thank you for sharing it with us.
Sure. Thank you. Thank you. Will there be any question answer session?
Uh,
Like if the audience is having any question, or they can connect me with
Yeah,
me on the
if
email.
there are any questions, I think they may ask now. Any queries or anything? Anyone? I think there are no questions or anything, sir.
Okay. Thank
Okay.
you very much for the wonderful opportunity. And I will again say stay safe, stay healthy, and use all the precautionary measures.
Okay, thank you, sir.
Thank you.
If you have an opportunity to interact with the resource person, if you're having any queries, you can ask, raise
Sure.
hand now.
Hello, sir.
Hello. Yeah.
Yeah, in the future prospects, you told about the additive manufacturing of aluminium.
Yes.
So, is it metal additive manufacturing?
Yeah, metal additive manufacturing, obviously, because it is aluminum.
Okay, and not composite materials, right?
Not composite. We can use wire feeder, wire type of additive manufacturing process, and
Yes, sir.
also people are doing with the laser cladding also.
Okay, fine.
Yeah.
Thank you, sir.
Welcome.
So moving on to the next one. Next, we have a keynote lecture on the topic Sustainable Initiatives, Institutional Possibilities and Assessments by Dr. Nidhi MB. Dr. Nidhi MB started her career with BTech in Mechanical Engineering, MTech in Industrial Engineering, and a PhD in Sustainable Assessment in Supply Chain Network under Carbon Trading Scheme, NIT Calicut. She currently works as a senior lecturer of Mechanical Department of MBSET since 2009. Her areas of expertise includes nature-inspired algorithms, industrial engineering, supply chain management, sustainability, education technology, innovative designs, energy management, energy efficiency, ergonomics, etc. Dr. Nidhi MB, I invite you to take over the session.
Thank you for the nice words. I hope I'm audible.
Yeah, you're audible. We can hear you.
Let me try and share the screen now. I think I'm not able to.
Excuse me, Nidhi ma'am. Sorry for
Yeah,
interruption.
you want Mr. Harris, Dr. Harris is
No,
here.
ma'am. No,
I
ma'am.
think
No, ma'am.
is it?
Harris, sir.
Hi, I absolutely did not realize the connection was
Okay,
dropped,
sir. Okay, sir.
and I kept speaking.
Okay, sir. Okay, sir. Nidhi ma'am, can I take over to him?
Yeah, sure. Please go ahead.
Thank you, ma'am. Thank you so much. Harris, sir, we already given introduction, so the stage is yours, sir. You can deliver the session.
All right. So did you hear any of the presentation or not at all?
No, sir. While starting,
at
it
all.
gets shut off.
All right. So I need to. Okay. Let's see how this is going to work. I'll start again. Let me just see. Okay, so can you see my screen now?
Yes, sir. Your
Yes,
screen
sir.
is visible.
All right. So you haven't been able to hear any of this. Okay, I'll give the presentation again. I did not realize if there is, for any reason, there is a connection dropping. Yeah, I'll try to monitor my email. Okay, so you can hear me now, right?
Yes, sir. We can hear you.
All right. Okay. So again, thanks very much for the introduction. I'm so sorry about this. I really did not realize what was happening. So the introduction was, thank you very much. Thanks for your kind words. My name is Haris Makatsoris. I'm professor of sustainable manufacturing systems at King's College London, and I'm going to present you today a cross section of my work in automated product and process discovery for novel materials, combining artificial intelligence and robotic automation. So, I mean, I have, much like pretty much everybody in the audience, I guess, my background is in mechanical engineering, but I have worked for a number of years. I have worked as in a chemical engineering department, and my okay. Sorry, I'm just very, very conscious now not to lose you. So you can still hear me, right?
Yeah, we can.
All right, okay. So you know, my work and collaboration with chemists and synthetic biologists since my chemical engineering days have exposed me to a picture like this. So what you see on the screen now is really a typical laboratory. Okay, so you can see, and back then, when I started about 16 years ago working in that space, the picture has not changed significantly. There is a lot of manual work actually, which made me think, right, okay, so that might be a good opportunity for automation. So this could be the killer application in robotics, actually, and automation. So with this idea, right, I thought, let's try and explore what is it we could do in this space, because everybody working in this field, especially those who are developing new therapies, new drugs, and we have seen what is happening now. We are still in the middle of a very, very serious pandemic, and we all see now how important it is to get these innovations to the hands of the end users, the consumers, as soon as possible. But the challenge, working from a laboratory to actually producing at the scales that are required, I mean, it is a big challenge. Getting from the microgram scale, which is a typical quantity we're working on when we're discovering a new therapy, a new vaccine, a new drug, to the thousands of kilograms or liter, depending what your product is, that is required, is a really challenging task. And of course, at the moment, all these are very disconnected, and there isn't automation in all the steps. There is some automation, but not sufficient in all these steps. So then that calls for perhaps new thinking. And what if we had robot scientists? What if we had robot chemists? How would such a machine work such that it could take us from idea to discovery, and from discovery to large-scale manufacturing very rapidly? Well, it had to work iteratively, of course. We have to have some sort of a mechanism to help us create a new experiment, plan the new experiment. Then we need some platform, some physical platform, to run these instructions with minimal or no human intervention, give us the results, and then we're able to analyze the results, learn from these before we figure out what would be the next set of experiments to do. And okay, so one might ask, if we are to do this, right? Why should we do this? Why should we do this? Because we have established workflows right now. They work, they take a longer time, but that's fine. We do understand them, and we happily use them. But two key questions here. One is a more sort of high-level scientific question. The other one is more of an engineering practical problem to solve. So the first one is really to confirm our understanding. If we cannot make a machine to reproduce a phenomenon, do we really understand that phenomenon? So that is a very fundamental question. And as scientists, we should be able to, figure out whether we can answer this question or not. The second one is increasing productivity. So data analysis, high throughput, repeatability, semantic clarity are very, very important in anyone's toolbox these days. And unless we have means to actually get the data, analyze them very quickly, but then whatever experiment we do, we can play it back with confidence and get the same results, are very important. And of course, as scientists, where do we spend, where should we best spend our time in? Is it in, pipetting, handling liquids, or going through, huge Excel sheets, going through tables after tables of data, or just focusing on the creative aspects and coming up with the ideas to try very, very rapidly? So an engineering question and a very sort of sciencey question we can answer by automation. Now, I hope you're still there. Can I suggest leave a microphone on, so I know that there is some activity and the connection is live. Is that okay? All right.
Yeah, that's okay.
Brilliant. Okay, thank you. Right, okay, so what are we searching? It is a different search space. Of course, once we have these tools, we should be thinking differently. And really, we have three requirements to satisfy. One is rapid execution. And of course, that helps respond to markets faster. That is getting innovations into the hands of consumers quickly. Efficient execution, and it is all about lowering costs and increasing productivity. And of course, directed control, which is all about meeting the specification. So what are the components of such a system? Rapid execution will require a rapid, reliable, and repeatable manufacturing technique, or a set of techniques, and of course, the physical embodiment of these techniques, that is equipment. Efficient execution is all about scaling up and having as much automation as it is logical. And then directed control, which is all about monitoring and feedback, getting the data and acting upon the data quickly. So these are the key components. So this is a piece of work we have done with a food manufacturing company here in the UK, where they wanted us to optimize one of their an aspect of their manufacturing process. So what we did, we used reinforcement learning, we used the Q-learning algorithm in particular, where we developed an agent which was able to create a set of actions to direct the actual process, the actual environment to do something. And that physical system would change its state, which we were able to measure and feed that back to the agent. And then there was a penalty reward function assigning a penalty or a reward to the agent, depending on the decision it made to come up with a set of actions. So it was very, very iterative, and we absolutely had no explicit description of the process at all coded in the agent whatsoever. And it was able to come up with an optimal process for this particular manufacturing problem. Thing is, though, you also need equipment, as I mentioned before. So process intensification is an emerging field in the space of chemical manufacturing, and that affords precise control of the factors that influence a process. And also this control allows repeatability and operator independence. So it doesn't really depend on how the operator sets up the machine. Just download the recipe, and the machine, time after time after time, gives you exactly the same result. This is a very, very important feature. Conventional techniques cannot actually do that. They do require a lot of setup, a lot of tuning every single time you charge a batch reactor to do the work that you want it to do. And of course, scalability is crucial. Whatever you do in the lab, you have to have a means, by means of the design, your geometry, your thinking, to take it to large scale rapidly. And there are some commercial implementations of these machines now available today that can take you from the lab to manufacturing very quickly. Okay, so you can have some, of course, AI techniques. You can have a really exciting methodologies to explore this very complex space. But let's look at things that as mechanical engineers we know of very well, and start from there. So design of experiments is a technique, as I'm sure you're all familiar with, or you have come across in some shape or form in the past, and its optimization counterpart, response surface methodology. These were techniques that have been developed in Japan by Taguchi some decades ago, have been used, especially in the automotive space, quite extensively, but they're just finding their way now into the chemicals design domain, which has not been the case until fairly recently. So we use these techniques, we apply these techniques in our space. I hope, Haris, I hope you're still there. Just to check
they're
in.
here. Yeah, we can hear you.
Excellent. Okay. All right. Okay. Right. So we did apply these techniques in the space of chemical product and process discovery, and this is a very good example. I mean, this is a very exciting new material. It is a functional material that changes its state by some sort of stimuli. So the particular one, it is intended to be used as a temperature sensor in coatings without using any electronics. So what it does, if the temperature reaches a certain threshold, then it changes color. And once the temperature is below the threshold, goes back to its original color. So it is fully reversible. So that is very important, right, for a coating, especially in applications where we cannot have the space or can justify the expense to have all the electronics, the control, and the thermocouples and everything that you need to require these days to take continuous temperature measurements. But the functionality of this material really depends on the size and morphology of the crystals that chemistry creates. And you can see here what I mean by that. On the left-hand side, you see a very conventional approach, or the result of a very conventional approach that has led to these crystals, and you can see it really is a mess. Okay, so really with this kind of quality, you cannot get the performance that you want from a coating. Excuse me. On the right-hand side, you see a very consistent size and morphology, which we were able to obtain using our methodologies and the kind of intensification techniques that I have shown you. So it is very important. So you see, with the precise control, you can control physical properties of your product. So the question is then, how do we use these clever optimization techniques to actually obtain the target product? Because the particular chemical system does give you different, as we have seen, right, different sizes, different morphologies, and therefore different performance. So how can we tune our product or dial the property, the physical property we're interested in? We did create a response surface methodology model, an optimization model, after mapping the space, and we were able to tune and select the right kind of material from that chemical system we wanted, which was the one in the middle. And you can see on the left-hand side, on the right-hand side, different morphologies and different consistency of the product. Thing is, you know, there is a lot more sizes, morphologies, options you get with this material. So finding V1, you could not really do it unless you had the platform to target the properties and also the optimization techniques that we have used to target it. So talking about optimization, I mean, optimization does imply iterations, especially with the systems that we're talking about now. There is a lot of black box optimization that is much more relevant in that space, because it is almost impossible to have models or equations in a closed form to describe these systems. So we use various algorithmic approaches. The popular ones actually are local sets algorithms, and they work really well provided that you are in the right region of the vast space you are exploring. And that can lead you to getting trapped in a local solution, which you don't want that. So this is part of another work that we did when we were trying to discover materials with, again, different physical properties, giving different colors, as well as a different molecular structure. And we use optimization techniques, and we did discover that you could either end up in a plateau, you could get in a local maximum or a local minimum, depending how the function you are looking at looks like, whether you're after maximization or minimization, whereas you would either be after that point or that point, really, if you're looking for maximization or minimization. So there is a need for global search, and evolutionary optimization strategies, and I'm sure you're familiar with this technique, can afford you to do this global search. We did apply these techniques, very easy to code, but they are very important in this particular space. And we're among the first in the world to apply these techniques in the chemical discovery space, especially combined and driving physical hardware, a physical reactor system. So why evolutionary algorithms? Because very well suited to the problem, capable of operating in unstructured spaces as we have, and especially when we have parameters which are undefined. So large number of parameters which we, are not quite sure about, and their importance in the process we are dealing with. Easy to develop, and I'm sure if you have been involved in that, you will know exactly what I mean. They are very robust, and they are very suitable for hardware-in-the-loop implementation. I mean, crucially, they are designed to do global search, which avoids getting trapped into these local features of our objective function, and they're very stable in the presence of noise. Of course, by themselves, they're not enough. We had to combine this global sets to sample large areas of the set space and combine them with local sets to further optimize or further explore local regions for the solutions that we really made sense. So that code really works really, really well. And here is an example. So this is a small drug-like molecule. And the interesting thing about that, it has an intermediate product that is a fluorophore, which means it gives a fluorescence signal if it is stimulated appropriately, or the final product, which does not. Okay, so this is very important because we can then recognize and switch from the production of one or the other, the intermediate or the final product, on demand, algorithmically. So what we did initially, we tried batch protocols. They have taken a very, very long time to complete the reaction. We have used, at the top here, we have used conventional flow protocols, which is the blue curve here. Worked really well in terms of getting a nice peak for the fluorophore, but then the reaction was taking a very, very long time to complete it. It took hours to complete, and it wasn't even completed after several hours. And then we used the platforms, the new manufacturing techniques that I have shown you earlier, which were able to converge very quickly complete the reaction. But then we observed that we were not able to get the same peak for the fluorophore, and we asked ourselves why. So we did apply these techniques. We were absolutely certain that we were trapped in a local solution. So we did apply evolutionary strategies to really identify those conditions that could get us to that point. And in fact, we were able to surpass that point in terms of the concentration of the, or productivity as it were, of the intermediates that we were looking for. So that worked really, really well. And then the question was, okay, fine, we can do all that with chemical systems, small molecules, and so on. But how about, in bioprocessing and sustainable materials such as bioplastics, or ensure food security or energy security. So these are very, very important materials now. Thing is, current manufacturing methods require huge space. They're very unpredictable, very unreliable, and therefore it is very, very expensive. So again, we use this methodology, the optimization, the rapid process intensification, and everything connected in an optimization loop, as I have shown so far, to see what we can do with that system. We work with a company to do this kind of work. And starting from the lab, we were able to actually, compared with existing techniques. So the graphs on the right-hand side with the lower peaks are all existing conventional techniques that are used in practice today. And we compared it with our methodology. So you can see two things. Number one, the peaks are much higher, which means you get a lot more denser cell cultures. This is very important because that translates directly in how much product you get out of it. And also the other important thing is you have a left shift of these graphs. That means we get to the peak a lot faster than with conventional methods. Okay, so that was very important. That was in the laboratory. I hope, Haris, I hope you are still there.
Yeah, I'm here.
Excellent. Okay, cool. And then the question is, how do we scale up? Okay, so we were able to scale up from 100 ml, which was the previous slide, the previous picture I have shown you, to a series of 10-liter reactor systems into a 4,000-liter pilot plant. So it's a very big pilot plant, actually. And we were able to scale up in one step, so no intermediate steps, literally in one step, by literally taking the process from the laboratory and playing it back with almost no modifications to the larger scale and getting, as you can see here, getting a very similar performance. That was significant. That is really a game changer. And we were able to achieve that with new manufacturing techniques, with automation, with optimization and algorithmic approaches to allow us to achieve that. So I have shown you a cross-section of the work we have been doing over the years in that space. And importantly, I think I have been able to demonstrate how we can combine engineering with automation, control, and algorithmic approaches, artificial intelligence, to allow access to a rich parameter space to help us identify solutions to very real, practical problems or real world problems. All the examples I have shown you, they are really either done by companies or there was an ultimate goal to actually come up with some sort of a material that would be used in practice. I have demonstrated the workflow that addresses the concurrent product and process discovery and helps solve problems that can accelerate innovation in new materials. And also have shown you how we can go, especially for more strategic areas like bioprocessing, how we can very quickly go from lab innovations to larger scales. And that was really, I mean, that kind of work is really a game changer. However, the challenge is still these technologies, these methodologies are still new, and although we have shown anybody, I mean, you can show that somebody can get the job done faster and quicker, as the cartoon shows here. Still, there is a lot of conventional thinking, especially by decision makers. It is really difficult to get past this conventional thinking, but I think we're getting there with the demonstrations we have done, the experience we have collected over the years. We are able now to change and make sure that these ideas find application in practice. Right. Okay. So at this point, I would like to thank all my collaborators, my team, and by no means this is not an exhaustive list of collaborators. These were the people who have worked with us in the work that I have presented here, but the list of collaborators is really considerably longer. And at this point, I'd like to thank you very much for your attention. I'm sorry about the glitches with the connection dropping. Now, if you wish to, please feel free, hook up with me either through LinkedIn or Twitter, or just drop me an email and let's find out whether we could collaborate on a project. So I'd like to thank you very much. And I'd like to pass over now to the chair of the session. I think Harish is you now.
Yes, sir. Thank you, sir. Thank you for the wonderful session, sir. Irrespective of this time schedule and technical issue, you have delivered a wonderful session to us. We are very well honored for that. The session is open for queries. If you have any queries, you can discuss with the professor.
So we have seen several online articles regarding your inventions regarding COVID resistance. Can you brief some of your achievements during this period?
Yeah, well, thanks very much for that. What I wanted to do this presentation, I wanted to focus on the work we're doing in materials, and especially sustainable materials, in particular with the last piece. But yeah, we have done a lot of work in the area of COVID, especially, or in particular in vaccines manufacturing. And we have used exactly the same methodology. We used process intensification, we combined it with computer control. We have not gone to the optimization stage yet because this work is very new, but using same methodologies, the same platforms have allowed us to move very quickly and deliver process innovation in the space of the manufacture of these prophylactic agents very, very quickly, which was really exciting development. It was a very exciting project, which is of course still ongoing, but we were very happy that we were able to contribute towards addressing this very horrible situation we are at the moment.
Thank you, sir.
Thank you, Professor, for the wonderful session delivered to us.
Thanks very much. Okay, well, again, thanks very much, everybody. It has been a pleasure and an honor to have been invited and present to you. I know it is after lunchtime now, and I know it is not the easiest time to listen to all that stuff. But once again, please feel free if you wish to hook up with me. You know where to find me now, so I would be happy to collaborate. Okay, thanks very much, everybody.
Thank you, sir. Thank you. Gokul.
Yes, sir. So moving on to the next keynote lecture, it will be done by Dr. Nidhi MB, who's going to present on the topic Sustainable Initiatives, Institutional Possibilities and Assessments. Dr. Nidhi MB started her career with a BTech in Mechanical Engineering, MTech in Industrial Engineering, and a PhD in Sustainable Assessment in Supply Chain Network under Carbon Trading Scheme, Calicut, Kerala. She currently works as a senior lecturer of Mechanical Department of MBSET since 2009. Her areas of expertise includes nature-inspired algorithms, industrial engineering, supply chain management, sustainability, education technology, innovative designs, energy management, energy efficiency, ergonomics, etc. Dr. Nidhi MP, I invite you to take over the session.
Thank you, Gokul. Thank you for the nice words. I hope I'm audible, and I will try
Yeah.
to share the screen now.
Yeah, we can hear you.
Yeah. I hope the screen is loaded.
Yeah, it's visible.
Thank you. At the outset, I would like to thank Dr. Rajesh and team at WISAT for giving me this opportunity. And it was according to Dr. Reddy's suggestion as we got into a discussion on what we want to convey. We probably took a little bit of lighter mode from the industry and the research lab kind of a discussion for keynote that you have been experiencing maybe since yesterday, since the conference started. So this is more into our kind of an institution where what we can do or what are the different initiatives that could be possible from as a faculty through students, what all can we achieve. These are the things that we'll be exploring today through this session. And today being the Earth Day, let me wish you all a happy Earth Day and request you all to take a moment of remembrance to the nature. I would like to begin with these words from Chandogya Upanishad. Says, as far as the space extends, so is your heart, so is your sun and moon, and so is what we perceive, and so we move on to the stars. And whatever is there in the world is same as inside the human being. This is a very elaborate version of the complete ancient Indian wisdom that is conveyed through these lines, and this is now being proven by the quantum physics also. Let's celebrate the Earth Day, and it's indeed a pleasure talking to you today on sustainability on the very same Earth Day where we need to attribute a lot of tribute to the Mother Earth. Looking at some of the world-class institutions which have already moved into sustainable initiatives, I would like to, share a few points here. So this is one just line which will cover entirely kind of a summary of today's discussion, what we want to show. So as far as possible, an institution always aims to be sustainable in terms of the research, teaching, and the activities that are taken in the campus, the student experience, and provide with the community service that are involved. Our research definitely, according to Stanford, they say it identifies a lot of challenges and helps develop the critical solutions and create a lasting impact on the campus as well as on the world. So these two words are really important in terms of the students or the graduates that we bring out from the technical institutions. How many of them are really contributing to the campus and as well as society? This is one question we as engineers we need to look, especially in the context of sustainability. To quickly move into the sustainable development definition, many of you may be familiar, and many of these things probably we are doing as part of our life or day-to-day activities or as part of your work, knowingly or unknowingly. But the only thing what we are trying to do here is to connect to some of them and to try and bring some of these things into our campuses, or share what we are doing into other campuses. This is the whole objective of today's session here. So to coming back to the sustainable development, it says there should be a balance of economic, social, and environmental considerations in all developments while meeting the needs of present generation without compromising the ability of future generations to meet their own needs. So whatever resources or materials that we want to use today, we need to handle them judiciously so that it is available for the future generations. We're not going to create a burden on the future generations. To look at it was the definition that was brought out by Bertrand Commission, and then the World Business Council again on sustainable development has brought out another definition in terms of economic prosperity, and environmental equality and social equality. So look at the words or the combination of words. So it looks aims at definitely a growth in terms of economy because the countries needs to prosper. Then the quality of environment, definitely the air we breathe and the water we have for consumption, or the energy that we use. All these are needs and environmental consciousness, thereby thus provide a quality environment is a social responsibility for all individuals is what it means here. And the social equity. Social equity definitely means the whole earth and its inhabitants are equally responsible for each other in maintaining a livable space. And some of those initiatives by Stanford include, like, it's very interesting to see some of them. It is not that too difficult for us to implement, but mostly we see that many of the things are not in our campus. And it looks like a question of why we are not moved into this kind of a thinking. Though late, it is time that we start moving on to these kind of initiatives. So Stanford says, like, they are moving on to by 2045, their target is 100% carbon neutral attempt. So they are moving on to renewable electricity, and they are reached almost like to the current status stage. They are almost reaching 69%, and by 2020 they were aiming for 80%. So already I think the COVID is already helping us with a lot of carbon footprint reduction. Energy and climate action also been looked at, and they have been maintaining a very good inventory levels, looking at the buildings and natural gas and the steam equipments they have been using into. They're also into emission reductions. Even by 2018, they reported a 72% of below the peak levels. So the tremendous efforts have gone behind in the past decade. That is why they are able to achieve below the average of 72%. They could maintain the emissions. So all these are possible inside a campus is a good inspiration for all others too. And they moved into the star rating. Then zero waste by 2030 is another aim where they right from the plastics to all the even the smallest material they're going to use, they're going to apply this. That is how the team works there. And there's a green campaign program where even 4,000 members are involved into the community engagement, creating awareness, and making the society learn and unlearn what the systems and things that they need to look at or bring out sustainable change in the world. The living lab concept, we have been just looking at Harris Lab. He has been sharing some of the aspects that we have been doing. A similar concept is again, happening in both the universities. And Harvard Living Lab, in their website, if you go, you can actually see about in a public tablet, and you see that there a lot of the energy emissions, energy uses, or in every office, what is the current scenario is being shared by them. So these are also possibilities in our own campuses, though we are not heavily into the great usages, but whatever little things that we do, we can think of even start quantifying it so that it helps for future sustainability assessments. So these are different possibilities, and higher education definitely hold a great role in creating a better change or a bigger change in the society or impact in the society in terms of education, research, or outreach through the various outreach activities and the various experiences the campus provides to its stakeholders, apart from its operations and higher education that is being offered. So basically, we need to get the qualified workforce into action, be it be the housekeeping staff, or be the professors that are involved, or be it be the decision makers. So at every level, be it be the strategic, tactical, or operational level, everywhere everybody needs to get involved. Then definitely sustainability is going to be in place, and definitely it is going to come up with a lot of impact in terms of economy, social, and sustainable lifestyle that can be imparted to the various stakeholders of the institution. Apart from the 6 Cs, which is the campus, curriculum, research, and community or operations, we can definitely focus much more on individual level, and where the behavior awareness and attitudes are given a much importance from the recent research studies as it reports to have a sustainable organization. So this is definitely an institutional process where every infrastructure that we plan or properly whatever infrastructure that you are existing, you still have a scope of moving towards sustainability. It's only a point where we start or how we start into. The rules and different policies and regulations definitely can be brought in, and systematic regulations and changes can also be brought into the system when we keep environment and economy in our priorities. This is basically a connected and synergic process where we can actually transfer all these research into the mode of application wherever we exist. These are all the different process that is done to achieve the sustainable goals, 17 sustainable goals. In fact, 7 of them, in fact, 8 of them are in the top priority, and towards the end of the presentation, we'll see which are those. And to bring you a glimpse of different models that has been followed in various institutions, leading institutions, we find that the Green University Toolkit has been widely used. We could even see that if you look at the latest reports and research findings that has been disclosed by, you can see that there are 3 major Indian universities moved into usage of Green University Toolkit. It is Cherry, CPRI, and the Calicut University from Kerala. So this is a very wonderful initiative, which I feel even our institutions of other institutions in Kerala can also look at. And EPIC, Seed, and carbon management are among the top. And IIT Guwahati also has used the SDG 2030 course, and they are on the process of implementation. They started with all the sustainability initiatives, whatever is possible, and it is fetching a lot of tremendous result in terms of sustainability. So only if this particular concept of sustainability become a part of the curriculum, then only we are in such a situation that we need to actually push our students through this process so that they become sustainable literate citizens or engineers or professionals. And the different way or the different way these institutions have used is you use change management as an engine, where you create you try to emulate the situations that are much needed for sustainability, and create those scenarios where you want to go for a paperless office, whether you want to have a blended learning option to maintain sustainability, or you want to go for a zero carbon campus. So whatever is your priority, that change management has to come as an engine of force or drive. Then definitely trust, engagement, and empowerment is equally important. The way you convince your colleagues, decision makers, and the students, it has to get transferred through the students and then to the society. Finance definitely needs a lot of reform in terms of sustainable aspects. Not just the economy that needs to look at, it needs to be supported in terms of sustainable initiatives. To foster the learning organization, definitely capacity building is important, and this is where our faculty and students will play a great role in reaching out to even the communities to create an awareness and to practice and to see that the system is in place. So one small example that can be brought in here is the new panchayat system. They brought in a system where every 3 months There are plastic collectors coming to your homes collecting plastic. So this is very much linked to the EPR system, which was released in it has come into force in March 2016. You see that every manufacturer needs to collect uh, at least the 70% of what they have been using as resources by the third year of their production, or the moment that the product is moving out to the market. From there, that point, within 3 years, they're expected to retrieve the post-consumed goods or the resources at least by 70%. Definitely, this has to become a part of the cultural change. Generally, it will become the need of the hour, and it gets implemented quite easily if it becomes your culture. And continuous improvement and leadership are definitely part of the initiative that we do. Every project or every subject that we teach, at least one faculty every semester takes an initiative to bring in the new part of sustainability into the campus. Definitely, there's going to be a change. So let it be any subject that we teach. Let's say, for example, most commonly, apart from the e-waste, usually a computer science engineer or electrical department may think, what more can we think of? Electrical definitely have a lot of scope in terms of energy, but apart from the regular routines, what different can they do? So why not create a app that can help in the collection of plastic waste or segregation? Or all this may be there, but in your locality, in your area, or in the village that your institution has adopted, can this kind of a facility help? That is where your innovation or your contribution comes in terms of technology transfer. This is the kind of continuous improvement and leadership that we are going to talk about. It's not really just within your institution or within you, but you're trying to transfer this to the people around you. And foster formal commitments and goal. Definitely formal documents may be needed, and it has to be taken as a common goal. The annual reporting and system thinking has to come in a holistic way at this point, where the indicators can be studied together, and performance parameters and key performance indicators could also be devised by holistic thinking, and a new thinking process and new beginning starts there towards sustainability. Following the various patterns, you could also see these are the different milestones that is achieved and reported by the Harvard. So journey to 1,000 miles definitely begins with your first step. So that has been proved. Institutional social responsibility, where the basic key is the transparency, and it is much important than profit, but profit definitely will follow after a long time. These are the different frameworks that are available for us to follow the sustainability. Definitely around in and around the industry, there have been a lot of changes, and if we understand these changes, definitely these kind of there is a need for sustainability is very evident from these kind of statistics that we can see. So almost 74% of the companies are already moved into these sustainability initiatives, and 45 of them are already into executive sustainability criteria. And these are the areas where some of our students will definitely find their job prospects too. And 76 of them are already started reporting. And if our student moves into an industry where he or she is not aware of this procedure or system, so what are the different quantification methods, what are the different analysis that are possible, how are she or he going to get an added advantage, or why, how will a company benefit? So the system thinking and data analysis is very important from this point of view. And we could also see that 49 of them already moved into the waste management, and product formulations are getting reformulated. And we see from the previous two speakers, keynote speakers, they already moved into sustainable materials and management. So there have been definitely a lot of conflict, and this conflicts definitely exist between a tug of war exists between economic growth but education is said to be the key, and definitely education institutes have a great role to play, because this is the reality of climate change that we see around us, and it's high time that we need a lot of change in these areas. And future cannot be so much stressed up with a lot of complexity on unsustainable practices, but there is an alarming need to address these. So definitely institutions have a lot of possibility in maintaining or creating a sustainable society through the students and various curriculum that we introduce. then foster innovations and create engineers who are responsible for ecology. And the engineering system also needs to cater to societal and entrepreneurs definitely has to be created instilling with 5R values. So even the right from even the green synthesis is what we call in the campuses on these students. Not only it's just not limited to chemistry, but also the 4 years of synthesis that can be brought into the students is a huge impact. And green offices are reported to have been made of a feasible and very wonderfully working system. It has been proved by the IIT Guwahati and Harvard. So we can also adapt to it. Almost recent reports say that 96% of them are sustainably conscious. But how about us, the Kerala institutions in Kerala? How are we all equipped for this initiative? And definitely we need to go through these complexities, but in a sustainable way. Definitely, this is how the sustainable society would look like with a clean air and fertile soil and healthy livelihood with optimum population size and halting. At least some of them, as we and our students as engineers will be able to help them through this in implementation. So these are the different determinants of well-being. These are, see, I would like to catch on these reduce the materials, water, and the reduce land use. Definitely rethink in terms of modern societies what they need. So the industry 4 or the industry 5.0, which is going to be in place, can definitely cater to this society 5.0 and above. So education definitely is part of the solution, and this is how a sustainable literate would understand the scenario. Like you can see that already some of them are proven people or leaders we have who has been sustainably living, and their life itself is a message for us to ensure that now this kind of a life is also possible, where you do a lot of teach and help and convey a message of inspiration for sustainability into others' life. Uh, Definitely, these are some different, thoughts which has been followed in, another institute. But I thought like I'll call upon only that particular part which can be shared here. So this is not come into any of the other discussions previously. So there's like a volunteer time of system. Can we also think of similar solutions which can be given to the faculty and students apart from the NSS and other professional body activities that we have? Can we think of these, activities to encourage different teams who are interested in different sustainable initiatives, and let's create interest groups and they can start working on these different initiatives into a very deeper level. So every year of progression they have deeper and deeper levels of implementation strategies and problems to look at, and definitely these teams will be able to help us build the institutional sustainability and its performance. Overall, the institutional sustainability mainly falls into three pillars. One is governance, environment, and the social aspect. So, social reporting and environment reporting and corporate governance becomes the main key themes there. And from there, the other sub options or operations starts, and we could build onto the institution possibility. Apart from keeping a bird path or creating the plantations or sapling planting on a Earth Day or a environment day, what are the different possibilities? These are the different possibilities a campus can do. So it definitely can have an environment campus which is locally economical and cater to the society with a social responsibility. This is what is envisioned out of education system, where there's a living laboratory model which is eco-friendly, and social experiments can also take place, and a lot of collaborations can be made feasible. Definitely, it should be helping with a public service in terms of regional planning, local. So, how many of the institutes move into helping out with the farmers and their agriculture systems? Very, very less. But in Kerala, being used to be an agrarian economy, and it is really struggling in the agriculture sector. So why not we look at those possibilities? Then with the whole ground of livestock created across the world, why are we facing poverty? So these are different questions that we still face in spite of the kind of technological advancement that we have. So lifestyle shifting or energy management, be it be the preservation of historical resources that we want to do, or be it be the preservation of economic ecosystems or green or open peace play systems that we want to bring in play, to be it be the energy consumption reduction in emissions or recycling that we want to do. Everywhere there is a huge possibility for each of us to get involved. And this is a small glimpse of from our campus where I hail from, the Basilis College, where you see the photo in the first slide. So we have small initiatives like the rainwater harvesting, then the biogas plant and solar plant being implemented. We also, apart from this, a small herbal garden is planned and cast iron recycling, and we are also catering to many of the engineering institutions for creating selling these cast iron blocks. A material recovery facility and incinerator are also being implemented, and we also won the Green Campus Award by the Indian Society for Technical Education. These are the small initiatives, but still quite a long way to go. We started with a small, green audit, and then we are planning moving on to the energy audit, and with a little more deeper analysis on how the footprints and water footprints, etc., can be implemented. Uh, so definitely, these are the goals that are in priority. No poverty, reduced uh, inequality, then sustainable and commutation, then responsible consumption, life below water, life on land, peace and justice, and partnership for attaining these goals. These are the going to be the 9 um, goals which are going to be of high impact by 2030. So we all need to work towards it. These are the engine of change that we can look at. See, the institutional capacities and policies needs to have a changing framework which is oriented towards the 2030 agenda. And you can see internationally, almost all the almost different universities in different countries have almost moved into a scenario where all the graduates needs to be educated on sustainability, and it's a high priority principle. And these are the different areas where you can actually see the higher education being involved in the sustainable mission. So definitely the mission of every educational institution in general is summarized here, but all these needs to be linked towards the sustainable value-based approaches and analytical problem solving towards sustainability, and sound technical and academical and behavior standards which are nationally and internationally acclaimed towards sustainability. Definitely competency is very, very important. So how to change subjects to competencies where the teachers will have to play a great role, and it has to be exceptionally distinct, and it should serve the fitness for purpose, so that you can be rest assured your student is definitely going to make a difference in the world. Apart from all this, there is going to be bodies like AICT and UGC. They are coming up with a new agenda to make sure that the green practices and green initiatives are in place, and almost all the campuses needs to mandatorily get adjusted towards having green initiatives. And for this, institutional sustainability assessments are be getting into the place as like MBA or a NAC or the ABET kind of systems that's coming in place. So this is again becoming a part of our system. Very soon or later, it is going to be in place. In other countries, it's already there. And so, apart from the quality teaching and professional exposure, sustainable quality assessments are also needs to get reported, and what are the different activities that we do, and whether it is an outcome based approach or development approach that we follow. This thing needs to be in place, and this is how the whole process is going to look like. Finally, everything has to reflect through the teaching learning process towards the outcome, which is definitely inclined to the sustainability initiative. So how it is different from accreditation, you could see that the assessors definitely will be giving us guidelines and suggestions, and try to help us get a plan of action towards sustainability. So this is more like they are like, though accreditation is there, ISA is going to be complementing whatever is recommendations that's given by the accredited body. definitely we do have a lot of challenges. See how to make the solar energy economical and make it available to those remote areas or those areas where it is solar energy itself is not accessible. Then provide the energy from fusion, then carbon sequestration, manage the nitrogen cycle, like not only the crop rotation, what are other feasible solutions which can be technologically transferred to achieve this cycle. Then clean water, urban infrastructure, health informatics, the reverse engineer the brain, okay, the better medicines. Even in COVID times, we have seen a lot of changes and innovations happening in this way. Then cyberspace, security, advanced personalized learning, and tools for scientific discovery are all these are challenges, but at the same time, these are all researched, opportunities for every institutions to work on and to collaborate and to bring in the change of innovation. These are the different references I've gone through. So it is, in fact, our world, not only your world, it's our world, and let's transform to the society. And thanks for your patient listening. If you're interested, you can reach me out here, and all the social media profiles are available in this QR code. Thank you for your patient listening, and thanks to Dr. Rajesh once again for giving me this opportunity to be part of this session.
Thank you, ma'am. Thank you for the wonderful presentation. We're glad that you were able to make such a presentation in such short time, and that you're able to take the time to present, share all that values with us. So we're really thankful and privileged to have you here.
Thank you, Google. I hope Google is the person I'm speaking to. If there are any
Yeah.
questions that we need to address, we can definitely address. Professor Sharavanan, I would like to say hi to you. He's here. I think he has visited our campus once.
Yes, yes. Hello,
Yeah.
hello, Dr. Nidhi.
Hello,
How are you?
how are you, sir? I'm good, thank you.
Thank you. Happy to see you. Okay.
Same here, sir.
Is there any queries you can ask to the madam right now?
This is an area we all need to work together. So definitely a collaboration and knowledge sharing definitely becomes part of us.
Okay, ma'am, thank you. I think there is no queries. We can move on to the next contributor session. Thank you for your valuable time, ma'am.
Thank you, sir. Thank you all.
So without delay, we can start our contributory oral presentations of today. We have our chair, Dr. Nidhi MP, and we have our co-chair, Dr. Raji CR. Yazin,
Yes, sir.
you can move forward.
Well, Dr. Nidhi MB started her career with BTech in Mechanical Engineering and MTech in Industrial Engineering and a PhD in Sustainability Assessment in Supply Chain Networks under the Carbon Trading Scheme, Calicut, India, NIT Calicut, Kerala. She currently works as a senior lecturer of Mechanical Department of MBCET since 2009. Her areas of expertise includes nature-inspired algorithms, industrial engineering, supply chain management, sustainability, education technology, innovative designs, energy management, energy efficiency, ergonomics, etc. Dr. Rajesh Sia is an associate professor in the Department of Mechanical Engineering at FISAT. He is an approved research supervisor for the PhD programs at APJ Abdul Kalam Technological University, Kerala, and he is also the member of curriculum committee at the university. He also received his PhD degree in mechanical engineering at Cochin University of Science and Technology, Kerala in 2008. Well, this session,
Okay, we can move on to the first paper. Participants, kindly note that we have a time limitation of 7 minutes. We should have to wind up within 7 minutes and 2 minutes open for the discussion. So total 10 minutes allowed for each participant. So I'm calling up the first participant, Charlie Chin Woon Siap from Swinburne University of Technology, University Malaysia, for his paper entitled Mode 2 Fracture Toughness of GFRP as a Function of Heating Temperature and Strain Rate. Over to you, sir. You can share your screen.
So can you hear me?
Yes, sir, you can. We can hear you.
Yes,
Oh,
yes.
and then can you see the screen as well? The share slide.
Yes, yes.
Okay, so I think without further ado, I will begin with my presentation. So good afternoon, everyone. So in these sharing sessions, I would like to share one of my research. Okay, so I am the co-author of this research. I'm representing the main author to present this paper. Okay, so the research will be on the mode 2 fracture toughness of the glass epoxy laminate composite under various heating condition and strain rate. Okay, so maybe we will start with the fracture toughness. So what is the fracture toughness? Fracture toughness in general, okay, can be described as a ability of the material with initial crack to resist the fracture and the crack propagations. Okay, so there are three the categorizations of the fracture mechanism can be split into three loading modes, which are mode 1, mode 2, and mode 3. Okay, so mode 1 is an opening mode, and mode 2 is a sliding mode, and then mode 3 is considered as a tearing mode. Okay, so in this study, we will investigate on the mode 2 loading. Okay, yeah. So these are the direction of the loading. Okay, so and then we will look at the mode 2 loading. Right. Okay, so so I move on to the previous study. So this is the previous study which are carried out by other researcher, right? Okay, so from this study, right? Okay, so for the third three author, they report that the fracture toughness is increased. Okay, so at higher strain rate. Okay, so and then, however, there are two author that deny the finding. Okay, so by conclude that the fracture toughness is decreased at higher strain rate. So yeah, so from their final outcome, the agreement cannot be reached on the strain rate dependent in the fiber reinforced polymer composite. So we will move on to the temperature effect. So for the temperature effect, okay, so Cowdy and Baumann state that the fracture toughness is relatively insensitive to the temperature. Okay, so Kim and E state that the fracture toughness is decreased with increasing the heating temperature. And however, the Machado and Frasin state that, okay, so the fracture toughness increase with increasing testing temperature. So with all of this run, okay, so all of the statement made by the previous researcher is draw my interest to a further study the fracture toughness behavior of the GFRP under mode 2 loading with the range of the heating temperature and strain rate. And according to the Machado and his team also reported that the mode 2 fracture toughness, okay, so is affected by the glass transition temperature of the matrix. Okay, so therefore in this research, okay, so I will study I will focus on the heating range between the room temperature and the glass transition temperature of the matrix. Okay, so for this research, okay, so the temperature will be set in between the room temperature 40 degrees, 60 degrees, and 80 degrees. So the strain rate will be starting from 1 mm per minute, 3 mm per minute, and 5 mm per minute. Okay, so move on to the sample preparation. So a 6-layer of the GFRP panel with approximately 5 mm thickness were fabricated by using hand up methods. Okay, aluminum sheets was inserted on one edge of the GFRP laminate panel after applying the third layer of the glass fiber fabrics to create a pre-crack opening. After completing the fabrication process, the control GFRP laminates panel will cure in room temperature, and then the rest of the panel will be placed in an oven with a controlled heating temperature of 40 degrees, 60 degrees, and 80 degrees for 12 hours. After curing, so the GFRP specimen, which show in on the right figure, will be cut from the large GFRP panels. Okay, so move on to the end-notch fracture test setup. The end-notch fracture Mode 2 fracture test was conducted according to the ASTM D7905M-14 standard. Sorry. So the displacement, the tested displacement rates of 1 mm per minute, 3 mm per minute, and 5 mm per minute, okay, was conducted. And the for the heating temperature effect, okay, so the heat treated specimen, okay, so will be tested under the control displacement rate of 1 mm per minute. Okay, so the mode 2 fracture toughness, okay, are calculated based on the direct beam theory. Okay, so I'll move on to the observation, okay, during the test. Okay, so as you can see from the figure, the sliding between the top and bottom plies, okay, here, so can be observed during the ENF test. The shear force at the sliding is caused by the delamination by the mode 2 fracture. So the crack propagations started after micro crack grew and merged at the crack tip. Okay, so crack tip is somewhere here. And then in the common, so the delamination under mode 2 involved in pure fracture in matrix and interface fracture between matrix and fiber. Okay, so and this we have the crack propagations. Okay, so highlight in red is the pure fracture in the matrix, and this behavior is can be observed in most of the tested specimen. The crack propagated in the yellow curve is considered as a interfacial fracture between the fiber and the matrix. So move on to the strand effect. Okay, so the G2 value at 3 range of the strand rate are plotted in the figure A. Okay, so the mode 2 fracture toughness is slightly increased with the strand rate increase from 1 mm per minute to 5 mm per minute. Okay, so the increase of fracture toughness at higher strand rate may due to the decrease of total damage at specific strand level when the strand rate is increased. As seen in figure B, the increase in fracture toughness is observed with increasing the strand rate. The inclined trend line show that the figure B, right, it is a solid evidence to prove above statement. So move on to the heating temperature effect. So for the temperature effect, the value of G2 increased as the specimen was heated to 80 degrees Celsius. However, the value.
So sorry for
the
interrupting.
G2
We have a
value was
time limit variation. So kindly conclude your session.
almost done.
Yeah.
Almost done. Yeah.
Okay.
Okay.
Done.
So was slightly decreased. Decreased at 60 degrees. And then the so overall, okay, so the G2 value distribution in the figure cannot strongly prove that the heating temperature is depend on the G2 value of GFRP laminate composite. Okay, so for on the other hand, so the overall heat treated specimen has a higher fracture toughness. Okay, so this may due to the finish chamber may impact by the internal stress of the composite by creating micro cracks and voids, as you can see out at the bottom figure. Okay, so the reduction in the micro cracks and void in the GFRP laminate composite when the heating the specimen during the curing, right? And then lastly, the scale effect. Okay, so the fracture toughness trend line is compared with the other research by normalizing the fracture toughness at 25 degrees Celsius. As you can see, the data show is so inconsistency of all the plots. So it can be concluded that the G2 value dispersion, okay, so to show that the heating temperature so independent on the G2 values. So in a conclusion, the results show a slight increase of the fracture toughness with increasing the strand rate. And the the dispersion of the value cannot firmly affirm that the temperature is dependent on the mode 2 fracture toughness of GFRP laminate composite. So the heat treated specimen was found to have a better fracture toughness performance compared to the control specimen. So these are the reference, and then that's all for me. So thank you very much. Yeah.
The session has been given for queries to the chair.
May I start, registration team?
Okay, thank you, sir.
Yes, ma'am.
Yeah, okay. Charlie, it has been a good work that you have done. So I have just a small question here to kindle the interest. You have seen an observation that with the increase in flexural stress, you see that there is a strain increase, and you also inferred this, related this to the inconsistency in the mode 2 failure pattern in temperature. So how do you justify this, or what are your inferences or reasons for
Pardon,
this?
can you repeat again?
You've seen increase in flexural stress with increase in strain, right?
Yes, correct.
Increase in the strain.
Slight increase, yes.
Yeah. What do you? What is your inference, or how do you give a
Okay,
reason
so
for this?
in the slide I already mentioned that the increase may due to the sorry. Okay, so it may due to the total damage at a specific strength level, okay, decrease. Okay, when the increase in strength rate.
Is that the reason for the inconsistency in mode 2 you want to relate it to?
No, it's not inconsistency, right? So you show that the for in the slide it show that the for the strength effect. Okay, so the G2 value is slightly higher. Okay, if increasing in strength rate, isn't it? Okay, so it proved that the total damage at the specific strength level, okay, so decrease, okay, when in strength rate. So when we observe with the fracture toughness, fracture stress, right? Okay, so as you can see, the fracture load, okay, is increased with increasing in strength rate. So that's why it can prove the above statement. Okay, the statement met. Yeah.
Okay, thank you.
Okay.
Are there any queries?
Any questions from the audience that you would like to take? Yeah. Any questions from the audience?
Yes, there is no queries actually. So moving on to next presentation, we have Ramdas.
Okay, so thank you very much.
Thank you. Okay, moving on to next presentation, we have Ramdasu Sainath from Indian Institution of Technology, Palakkad. He's going to present this paper entitled on the topic numerical study for drag reduction of airfoil surface using dimple pattern. Please.
Am I audible, sir?
Yes, you're audible.
Can you see my screen?
Yes, you are audible.
Yes, your presentation is visible as well.
Okay, sir. So can I start?
Yeah, sure. Start.
Good afternoon, everyone.
Yes, please start. Please.
Good afternoon, everyone. I am Sainath from Indian Institute of Technology, Palakkad. Today, I would like to present a numerical study for drag reduction of aerofoil surface using a dimple pattern. So as far as the presentation is concerned, so I would like to give a brief introduction about drag and drag reduction techniques. So I would discuss few outcomes from literature, and I will give my objective and my simulation methodology I have obtained, and I will discuss the results, and I will conclude the presentation. So before moving to drag reduction and drag reduction techniques, if you see what basically a drag is, so by the definition, the force a flowing fluid exerts on the body in the flow direction is called drag. For example, if we consider an aeroplane cruising in an air, the force experienced by the aeroplane in the direction of airflow is only considered of drag force. So the basically two effects that cause drag on a body are friction and pressure difference. So when we talk about total drag force, we take both friction and pressure into consideration. So the total drag force is drag force due to friction plus the drag force due to pressure. So why this drag is coming into the picture? So something is happening when the fluid is flowing over some curved surface or any surface. So as we can see from the first schematic, when the air is flowing over a curved surface, we can see the flow is being separated here. So some phenomena is happening due to this flow separation. So we can see what is that phenomena which is happening. So if we consider at certain point of time the flow is being separated, so before that separation point we can observe that we can have that we are having a negative pressure gradient, which we call it as a favorable pressure gradient. That is, the fluid will try to flow from high pressure to low pressure, which is obvious and feasible. So after this separation point, we experience a adverse pressure gradient, which is a positive pressure gradient. That is, the fluid will now try to flow from low pressure to high pressure, which is not feasible. So as we can see, the velocity profile changes. That is, some part of fluid will be recirculating here. So hypothetically, we say that to maintain the similar velocity profile, the boundary will hypothetically separate from here to here. So we call it the boundary has been separated, and we also call it a boundary layer separation. So due to this boundary layer separation, the flow is also being separated. As you can see from the animation here, due to the flow separation, we can see a lot of wake and eddy currents being produced here. So this creates a lot of vacuum here. So this tries to pull the body towards back, which is called as drag force. So if we see why drag reduction is needed, so there are certain surfaces which need low drag properties. Such surfaces are automobile vehicles, aircrafts, marine ships, and even pipelines which carry high pumping energy and high flow rates. So in all of the cases, we are trying to increase the efficiency. And in case of automobiles and aeroplanes also, we try to increase the stability also by reducing the drag. So we can see even the shipping industry has been losing a lot of power to overcome this drag, and a lot of money is also being spent on revenue to overcome this drag in aircrafts. So if you see these are some of the various drag reduction techniques. So first one is the famous technique like streamlining the shape of the body. The famous example for this is a aerofoil body. So in case of a aerofoil structure, we can see the separation region is very small. So the drag experienced by the aerofoil body is very small. So even though when we move on to the second technique, it's a type of technique where we use vortex generators to delay the separation. So even though the aerofoil is streamlined at a higher angle of attacks, in case of aerofoil also the separation is being taking place and a lot of instability is created on the wing. So if we install vortex generators on the aerofoil, as you can see, so these vortexes generate and they mix the fluid so that they energize the fluid well enough so that they delay the separation and they provide better stability to the wing. So inline to this vortex generation, there is another technique where we modify the surface of aerofoil with a 3D pattern. Like in this case, it is a 3D dimples on the surface which can act as a vortex generators. And one more fourth technique. This is a bio-inspired technique where here we try to reduce the drag due to friction. So we are trying to reduce the skin friction drag. So what happens is, in case of high turbulent flows, there are a streamwise cylindrical vortices are being generated. So due to this streamwise cylindrical vortices, a high amount of shear stresses are generated when they come in contact with the surface, which leads to a high amount of skin friction drag. So when we have a small projections on the surface of the body, so when the spacing is less than the diameter of the streamline vortices generated, so these streamlined vortices cannot be fit into the surface, so they get lifted up from the surface, and the contact between the surface and the vortex will be reduced, which thereby reduces the skin friction drag. So this kind of projections on the surface is basically found on the skin of the shark. So moving on to some of the important outcomes, as I have discussed in the previous slide, even though the airfoil is streamlined, as angle of attack increases, separation increases. So use of vortex generators help in reducing the separation region. And in case of friction drag, if you want to reduce, use of riblet surfaces help in reducing the friction drag. So based on our application, we can go based on our need. So in order to have detailed understanding of drag reduction, further investigations are needed on surface modifications like 3D patterns. So the object of my study is to study the effect of angle of attack on separation region in case of aerofoils, and to investigate the drag reduction on aerofoil with 3D pattern on surface through simulation studies. So this is the simulation methodology I have followed. This is the basic CFD simulation. So firstly, we need to consider the model and domain for our problem. Then we need to construct the mesh for the model. Then we need to apply our suitable boundary conditions and select the solution model. Then we'll go for checking the convergence. If we are happy with our convergence, we'll go for post processing and publish our results. So if we are not happy with our convergence, most probably the problem will be with our mesh. So we will go rectify our mesh and go through the steps again. So moving on to the simulation study. So for the basic simulation study, initially we have considered a NACA 0018 aerofoil profile with a 16 centimeters chord line, which is a symmetrical aerofoil profile. So two models are considered. One is a plain profile, normal profile, and one profile is with a single dimple on surface. So this is the flow domain considered. So this is the inlet and this is the outlet. This is the model you can see. So these are the basic dimple dimensions. The dimple is a semi-ellipsoidal dimple. So this is the basic mesh considered. So this is an unstructured tetrahedral mesh with inflation layers around the aerofoil, and this is how the mesh looks around a single dimple. And as you can see, these are some of the assumptions and boundary conditions used for the simulation study. So the boundary conditions are velocity inlet and pressure outlet. So as you can see, the Reynolds number is 3.2 into 10 power 5, which signifies that it is a turbulent flow. And the solution model used is a Spala-Talmana turbulent model, and it is tested for various angle of attacks. So as we move on for the comparison of velocity contours, for a lower angle of attacks at 0 and 5 degree of angle of attacks, we can see there is no significance in using this single dimple over here. So as we can see, the separation region is not changed any much. So we can say it is not significant enough for this dimple at lower angle of attacks. As we move on to higher angle of attacks, we have used only a single dimple here. So there is a small decrease in separation region we can observe from here. So we can conclude that this shows that effectiveness of dimples will come into picture only at higher angle of attacks. So you can also
kindly conclude your session, Ram.
Oh, okay, sir. I am about to complete, sir. So you can also quantitatively see that these are the results obtained, and you can see the vortex being generated. So in order to improve the study, we have extended the model to an array of dimples. So the similar kind of mesh and dimples, similar kind of mesh conditions are considered, and the assumptions and boundary conditions are taken. So these are the contours obtained for 0 and 5 degrees. So similar to previous results, so lower angle of attacks are insignificant, and at higher angle of attacks only we can see the effectiveness of these dimples. So quantitatively also we can see as the angle of attack is increasing, we know the drag coefficient should increase, so it is increasing. But comparatively, when we use the model with dimples, we can see the model with dimples is showing lower drag coefficient. So we can conclude that at a higher angle of attacks, these dimples come into picture, thereby reducing the drag force associated. So these are the conclusions. Like to decrease the drag on aerofoil, we can go for modifying the structure with modifying the surface of the aerofoil with 3D dimples, which can act as vortex generators. So these vortex generators energize the air and delay the separation. So this is some prototyping study we have done. So we are planning for experimental testing also. So this is the model we have printed using FDM based 3D printer. So these are my references. Thank you.
Thank you, sir. The session has been given queries to the chair.
Okay, good work, Sainath. And so, at what stage are you in your work now?
Currently, I have finished my simulation work. We are
Mhm.
planning for experimental work, but due to the COVID situation, it's difficult for going for experimental. We are waiting for it for do our
That is,
experimental
what are
study.
the different materials you have decided to have it tested? Is it only the 3D printed material that you're planning right now, or you have a
Actually, we are planning only for 3D printer material because I am not considering any strength-based analysis here. Only I am considering the flow-based analysis. So the material is not an issue for me. So I'm basically using a PLA material, just to low-cost material to print the prototype and just check for drag reduction.
experimentally prove it? Okay, okay,
Yes.
thank you. Over to audience. Any questions?
I think there are no other queries. Thank you for your presentation, sir.
Thank you, sir.
Moving on to next presentation, we have Astosh Kumar Gupta from Maulana Azad National Institute of Technology, Bhopal, India. Is going to give a presentation on his paper entitled Effect of Process Variables on Performances Measured in Filament and Pellet Based Extrusion Process. So please.
Okay, sir. I am audible, sir.
Yes, you're audible. And your presentation is visible as well.
My name is Ashutosh Kumar Gupta. I am here to present the presentation of effect of process variables on performance measured in filament and pellets-based extrusion process. This work has been done under supervision of Dr. Mohammad Tawfiq, which is also the project in charge of this project. The content outline of this presentation is the introduction, then literature review on the filament-based extrusion process, pellet-based extrusion process, and the research gap and conclusion, and the acknowledgement and the references. First we start from the introduction. What is the additive manufacturing? Additive manufacturing, also known as layered manufacturing, rapid prototyping, and 3D printing. EM uses additive manufacturing uses the 3D digital model created by CAD that sliced digitally to fabricate parts in layer by layer manner. Addition of the metal layer can be done by in many styles, including extrusion, curing, and welding, and others. Type of material type of additive manufacturing can be classified into binder jetting, direct energy deposition, material extrusion, powder bed fusion, sheet lamination, and wet photopolymerization. But in this work, I have studied the material extrusion process. Material extrusion is widely used 3D printing because of the availability and low cost of the raw material and straightforward fabrication of complex parts. In material extrusion process, metal is selectively dispensed through a nozzle. The schematic diagram of the material extrusion is shown in the figure. This is the schematic, that this is the nozzle and this is the diameter, and this is the layered by layered material deposited to form a product or a structure. The material extrusion process can be classified into filament based material extrusion and pellet based extrusion process. And the advantage of the additive manufacturing process is, unlike the casting and forging requires the specific tooling to produce a part, additive manufacturing does not require any specific tooling. Additive manufacturing reduces the cost and production time by eliminating process step. Advantage in the additive manufacturing reduces the cost of object and devices in automobile, aerospace, medicine, and the consumer products. Some of the disadvantage of the additive manufacturing is the improvement in the geometrical accuracy and the surface quality of the part is major issues in 3D printing. Thus, post processing of part may be required that induce the machining to reach the desired shape and size. And this is the schematic diagram of the first two is the filament based extrusion process, and second is the pellet based extrusion process. In the filament based extrusion process, um, this is the and the I have measured the effect of the process variables in the from the previous literature review. The effect of the printing speed on the performance measured. The behavior of tensile strength, density, and the surface roughness at different printing speed is shown in the figure. The result was obtained that increase in the printing speed reduces the tensile strength and density as well as because of the poor bonding and less forming time available. Surface quality in the horizontal direction enhanced by the increasing printing speed, but in the vertical direction surface quality decreases. It happens because the thinner layer formed at the higher temperature. The effect of the process vary on the printing speed on the performance measured. Hamza and et al. Used Taguchi to orthogonal array for designing an optimization experiment. The result shows that dimensional accuracy is significantly affected by the printing temperature as well as the printing speed increase in print. As the printing temperature increases, dimensional error decreases, as shown in the figure. And one of the air gap process parameter has been measured to affect the process performance measured. Mohammed and al. 30 investigated the loss compliance, storage compliance, and the surface characteristic by varying air gap. The experiment was designed using RSM and artificial neural networks is used to investigate the performance. The temperature dependent, these are the storage compliance, surface characteristics, and loss compliance is the temperature dependent mechanical property which is increases by increasing the air gap. This is the three type of air gap we can use. The first is positive zero air gap, and second B is positive air gap, and C is the negative air gap. This is the raster performance of raster gap on the performance measured. This is the figure taken from the Gavisa and Lemon 2012. Flexural modulus in the highly affected by the changing raster from 0 to 90. First A is shown the zero deposition of the layered at the zero raster angle, and second is so the 90 degree at the raster angle 90 degree. That it is clear from the figure 0-degree deposition considerably improved the flexural strength. The reason behind this is the part made with 0-degree long rasters has been deposited in the length of the part, and the load had to cut all the rasters because before the part break. And after in the pilot extrusion process, which has been very less has been work done, has been performed till now. The bus this is the road gap on the road gap performance measured by Reddy et al. And for measuring the road gap, the experiment was designed using box Bacon design of experiment, and investigated the surface finish and the strength of the considerably low.
Sorry,
load gap.
Ashdod, for the interruption. We
Yes,
have
sir.
a time limit duration, so kindly speed up your presentation.
Okay, sir. And at last, the observed research gap and our conclusion is the surface roughness, dimension, accuracy, and the important characteristics related to the surface morphology, and surface roughness, dimension, accuracy, and the strength are the essential quality characteristic in the fabrication of a part in the 3D printing. Basic knowledge of how variables affect the quality. This needs to be extended to enhance the process capability, feedstock, and control. Thermal and mechanical property of filament and pellet also play an important role, but supplier does not provide a specification of feedstocks beside a nominal diameter and size. A small variation in commercial filament and pellet have been never investigated, but it would expected to affect the deposition and the quality. The majority of the published work has been reported in the filament-based fabrication in material extrusion category. Very less work has been done in the fused pellet extrusion process. Furthermore, limited research focused on the optimization of process variable for the response measured. This is the references, and this work has been sponsored by DST Serve DST project under the grant number this. Thank you, sir.
Thank you, sir. The session has been given queries to the chair.
Ashutosh, I believe this was more of a review presentation that you have been giving us. And
Yes, ma'am.
would you like to highlight, because most of the industries are now using the pellet extrusion process right now,
Yes, ma'am.
and
Yes, ma'am.
we'll see that they'll be soon shifting into the automation in terms of 3D printing and other additive manufacturing processes. But in this
Yes, ma'am.
context, what according to your review, what are the different performance parameters or performance variables that you would like to highlight are important concerns in this journey?
Ma'am, actually, there are many software-based and hardware-based filament process variables available in the software-based variables can be categorized on the basis of softwares, which can be controlled by softwares. But some of the
Keeping apart the software part,
Yes,
if
ma'am.
we are in this process of shifting from the extrusion, or let's take the case of extrusion,
Yes,
what will
ma'am.
be the performance parameters that you would suggest are most important if we are looking at the correct structures?
Ma'am, we are looking for the hybridization of filament as well as the pellet based extrusion process.
Okay, any performance parameters you have identified to merge both these two things while
Yes,
you are
ma'am.
hybridizing? Yeah.
We are working on the quality of improving the quality of product by measuring using the filament and the pellet based extrusion, and we have a hybrid
No. So
to.
these are all methods that you're telling us. What I
Yes,
was
ma'am.
asking is the different performance parameters that you have identified, if any. Okay, I think the time is also going. If you can quickly throw light on the variables, it will be great. Otherwise, let's take
Yes,
it up. You
ma'am.
can post in the chat. Yeah.
We have focusing on the quality of the product. The quality of product majorly included the surface roughness and dimensional accuracy and the strength of the part.
Okay, thank you, Astosh.
Okay, ma'am. Okay, ma'am. Thank you, ma'am.
I guess there are no queries left. So moving on to next presentation. Thank you. Thank you for your presentation. So moving on to next presentation, we have Joshin Fat, Swinburne University of Technology, Malaysia, who is going to present on his paper entitled Aeroelastic Performance Analysis of Horizontal Axis Wind Turbine Swept Plates. So please.
Can you access my screen?
Yes, I can see your screen.
Okay, fine. Okay, our topic aeroelastic performance analysis of horizontal axis wind turbine swept blade. This is Saravana Kannan. I'm from Swinburne University of Technology, Sarawak, Malaysia. This is our student paper. I'm presenting on behalf of my student. I'm one of the supervisor for this research. Okay, what do you mean by aeroelastic? Aeroelastic performance of the wind turbine. So definitely you look at the wind turbine. So there is fluid and structure interactions. Fluid structure interaction, that is FSI, that means aeroelastic. So the performance analysis of the wind turbine for alternative blade, for the current blade is unswept blade. So we are looking for the new blade. The purpose of looking for the new blade to reduce the aeroelastic instability. Okay, that is the main issue we are going to address through this paper. Okay, so outline for this paper, introduction, literature review, methodology, results and conclusions, everything we have. Okay, so when you look at this figure, current wind turbines are looking for more than more than 5. This is 7 megawatt and this one 10 megawatt. Those more than 5 megawatt wind turbines, they actually normally have the rotor diameter 120, greater than 120 meter. If you're looking for 10 megawatt, 145, it's a very big here. So the rotor diameter is this, the rotor diameter. Okay, so in the rotor diameter, but the wind direction of the wind coming here, and the rotor axis is here, this is the rotor diameter. But if we cannot get the wind speed exactly in the rotor axis. If it is exactly in the rotor axis, the yaw angle, this angle is 0. If it is 0, that is good one. But it's not possible to get the wind direction in the 0-degree yaw angle. It's the possibility to get different because of the wind pattern in the different geographical locations. So why, if we have different angle of the yaw angle, I mean the wind pattern, what happened to the normal wind blades because of the fluid interaction? Because definitely instability. Okay, so introduction for this one, the capacity of the commercial wind turbines has increased very big, more than 120 meter rotor diameter with a more than 10 megawatt power. Okay, so increasing the rotor length and the rotor diameter causes significant deflections. At the same time, leading the unsteady aerodynamic load distribution, affecting the structural safety. So that issue affecting the structural safety and structural stability of the wind turbine. So what you do, how do we control, if you still have the structural stability, what happened? Definitely the performance of the wind turbine reduced. At the same time, failure. We are ready to face the failure. We need to spend a lot of cost, money to overcome the failure. So when we're looking for the horizontal axis wind turbine, which is operating under yaw condition. Yeah, of course, I said the yaw condition. Yaw condition means the yaw angle. So definitely it's require yellow electric performance analysis for different yaw angle. Yaw angle is the angle, as I already told you, the alpha. This is the yaw angle. Okay. So when we're looking for the aim for our objective to analyze the aeroelectric and the flow structure interaction performance of the horizontal axis wind turbine for different yaw angle. So objective to investigate the relationship between yaw angle, aeroelastic performance of the wind blade, and to analyze different angles, 0 degree, 10 degree, 30 degree, and 60 degree. And we fixed the wind speed as the 10 meter per second. Of course, wind pattern is different because minimum 7 meter per second is required to rotate the blade for the 120 or more than 100 rotor diameter blades. So for the 10 meter per second, how actually the aeroelastic behavior looks like using computational fluid dynamic approach. So we have analyzed for the swept blade, two different alternative blade. Okay, so when we look at for the literature review, aeroelectric performance analysis, the integration of analysis of the aerodynamics and structural dynamic model. Example for this study, aerodynamic analysis for power generation and for structural dynamic analysis for the deflection in the blade, that is the vibration in the blade due to the different angle. So yaw angle is the angle or also known as yaw error, angle between direction of the wind and the axis of the rotor. Yeah, exactly that angle. So direction of the wind and the axis of, this is the axis of the rotor. If it is different, this is the angle, yaw angle, either alpha or gamma, sometimes they use pi. Okay, for various this yaw angle, how the behavior, aeroelastic behavior looks like this. Okay. So for our reference, the previous study by Dow et al. 2017 did the aeroelastic performance analysis for unswept blade, no swept conditions. Okay, so and they actually analyzed for different angle for 0, 10 degree, 30 degree, and 60 degree yaw angle. So that condition we adapted for our new blade. Okay, so this is our new blade that is with the swept blade. So what do you mean by swept blade? This is okay, little the front, front part little sweeping. Okay, so the sweep curve presented by the Loward and Zutek in the year 2016, taken for analyze the higher aerodynamic performance. That blade specification we adapted for our analysis to analyze the aeroelastic instability. How are we actually able to create, reduce the deflection? How we able to increase the power generation? That is our interest for this research. Okay. Okay, so these are the data collected from that literature for the swept blade and taken for our design analysis. This is the geometric design for our swept and unswept blade. So actually, this is our new design blade, and we still taken the old design blade also. That is the unswept blade already analyzed by different others. Okay, taken for our reference. So this is the left one is the unswept one, and the right one is the swept one. And this is the computational domains we used for analyzing our blade model, located by 1/3 length of the front base, defining, and mesh generation we did for the coarse mesh and the fine mesh, and data for the computational simulation for the various viscous model, I think SST, CSS model, turbulent model, boundary conditions for the wind turbine. Well, actually, we fixed the wind speed 10 meter per second and analyzed for different yaw angle. Okay, so we did for both the CFD and the finite element analysis. And validation of the before actually do the simulation, we did the validation for the meshing and achieved for 4.1 times 10 power 5 independent testing. I mean, mesh validation testing we did for the accuracy for the simulation, and did the aerodynamic analysis in the computational ANSYS Fluent, and that results obtained from the aerodynamic analysis, that is the Fluent result converted into FEA analysis to analyze the deflection in the blade. And for different yaw angle, this is our CFD analysis result, the power produced, and this is the power produced for the either the analysis for the unswept blade, the normal blade. And if you're looking for the swept blade, the power generation is very high. If you're looking for the 30 degree angle, this is 251 kilowatt, but this is able to produce higher power. Okay, for the swept blade. The similar effect for the power generation of unswept and the swept blade. But the thing is, when we compare for the yaw angle, there is a significant, negative effect on the power generation. So if we are varying the different angle, negative effects only we notice. But anyway, the power generation is very high. And for error comparison for the unswept blade and the swept blade, comparing with the literature reference, okay, so they actually have the similar power generation. And for the deflection for the blade, anti-static structural analysis, given the total deformation computation by the contour plot, for the deflection for the swept and the unswept blade, it looks, it's almost close to this, but no big variation. But anyway, the power generation is good. So anyway, the unswept blade or the swept blade, both are capable to generate a better power for 30 degree. If you beyond the 30 degree, definitely, negative effects happening. For your angle for 0 to 30 degree, this is the deflection. And we notice that deflection for this is for 0 degree, and this is for 0 degree angle, but 0 degree is not possible to get the wind direction. And when we're looking for 30 degree angle, almost close to this, your angle at the 60 degree, the minimum deflection noticed, lower normal of force. At the same time, yaw angle for the 0 to 30 degree, the yaw angle increases, the deformation increases, and increased normal force we noticed. And finally, for the structural dynamics comparison for the unswept and the swept blade, almost close to up to 30 degrees, similar one, but beyond 30 degree angle, swept and unswept having different deflections. And the conclusion for this presentation, aeroelastic performance analysis of the horizontal axis wind blade, swept blade under yaw angle, different yaw angle done. And the yaw error has the negative effect on the aeroelastic performance of the swept blade and has a similar trend as of the unswept blade. And swept blade has a better aeroelastic performance under the yaw condition compared to unswept blade in terms of higher power, rotor power, and low rotor deformation. For the higher stability. And these are the information for the future work, the future investigation of the aeroelastic performance of the horizontal axis wind turbine swept blade under for the different yaw condition, analyzing the thrust, aerodynamics, and the stress acting on the swept blade need to be done. Actually, my student, they are working currently in this research now. And also the transient state simulation using the full version for the ANSYS, because currently they used student version only because with the limited access, and more accurate and desired result we managed to get. Thank you. Are you okay?
Thank you very much, sir.
Is the timing okay?
Yes.
So any questions? I'm happy to
Okay,
answer.
good. Nice presentation, sir. Looked like a very promising results. All the best to your team and yourself.
Okay, thank you.
The session is open for audience for any questions. Any questions from the participants?
So if you have any question, you can email me. I reply to you, or our team reply to your questions. Thank you.
Thank you for your presentation, sir. Moving on to next presentation. We have Abhishek Patel from Maulana Azad National Institute of Technology, Bhopal, India. Is going to give a presentation on his paper entitled Nanocomposite Materials for Used Filament Fabrication. So please.
Good afternoon, sir. Am I audible?
Yes, sir, you're audible.
Sir, is my
presentation is also available.
Okay, sir. Sir, I'm Abhishek Patel from the Department of Mechanical Engineering, Maulana Azad National Institute of Science and Technology. I'm a PhD scholar there. And then this is my work on nanocomposite materials for fused filament fabrication. So the contents of this presentation are divided into the following subheadings. First is the research objectives, novelty of the work, introduction, literature review, validation, conclusion, and then references. So the research objective of this work are to carry out the literature review on non-composites materials for the fused deposition modeling and present all the information on the development of nanocomposites and how they enhance the material properties. So this is a review work carried out on the evolution of nanocomposites for the FDM to make use of advantage of nanocomposites for superior material properties, but very limited literature review is available, and hence a lot of scope is available for innovation and improvement of materials for the FDM realm. So 3D printing is mainly classified into three main categories: the powder based, liquid based, and the solid based. My work is concentrated mainly on the solid based. Now the solid based 3D printing is further classified as the filament based and the pellet based. In the filament based, a long plastic filament is fed from a spool to a nozzle where the material is liquefied and drawn on the platform where it immediately hardens again. Whereas on the pellet based, in this additive manufacturing process, plastic pellets are fed into the printer instead of traditional filaments. Now, the advantage of pellet-based extrusion is that the cost of the printing is reduced. So fused deposition modeling begins with the creation of model on the CAD and then selecting the best orientation, slicing the model, providing the layer thickness, and then the part's outer periphery is represented that could be scanned or loaded with various loading patterns to create the part. And the restriction of FDM is that the restricting material choice, component accuracy, mechanical performance are some of the limitations of the FDM, and these limitations restrict the use of FDM in practical applications. But the development in nanotechnology opened the way for the evolution of nanocomposites, which offers superior thermal and mechanical properties while weighing substantially less. So the literature review is carried out, and the literature review is divided into 5 main subheadings. The number 1 is the nanoclay-based composites. The inclusion of nanoclay improves dominant properties like modulus, strength, and thermal stability. Wang et al. Carried out their work in 2016, where they mixed organic montmorillonite in ABS, which is acrylamide butadiene styrene, for the FDM. So the uniform distribution of OMMT in ABS matrix limits the mobility of ABS, and this results in the increased stiffness and reduced break elongation. It also reduced ratio of thermal expansion, which reduced deformation and wrapping. Coppola et al. Carried their work in 2017, where they mixed nanoclay in PLA, which is polylactic acid. So the mixture showed improved crystallinity, and then the mix resulted in increased 15% elastic modulus. And their study was further carried out to see how the printing temperature affected the printing composites. The nanoclay additive resulted in chain orientation and stretching, which improved mechanical properties. So here in this figure, ABS and OMMT nanocomposites is shown, and we can see when the percentage of nanoclay or OMT was increased from 1 weight percent, 3%, and 5 weight percent, both tensile strength and elastic modulus were increased. The second category is the carbon fiber based composites. Thomas et al. Carried out their work in 2020, where the inclusion of GNP increased the surface area, and GNP and carbon fiber hold the polymer together, and this results in the increased ultimate tensile strength and electrical conductivity. And the increase in the ultimate tensile strength can also be seen from the figure. When the content of GNP was increased, the ultimate tensile strength was continuously increasing, but beyond 5%, the mobility of the metric was so limited that the printing cannot be carried continuously. So 5% was selected as the optimum. And Sofner et al. Carried their work where the carbon fibers were mixed in the ABS, and their work showed improvement in strength and stiffness. The next category is the carbon nanotube based composites. Young et al. Carried their work in 2019, but the carbon nanotubes, but the incorporation of carbon nanotubes in the PLA, this limits the mobility of composites, and hence 6% by weight is optimal for continuous printing. And the mix showed the increased tensile strength, flexural strength, and electrical conductivity. But the one drawback in this mixer was that the reduced material flow index. So 6% of carbon nanotubes in PLA was selected as the optimal. In the next work, Christ et al. Carried their work with the increase where they mixed CNT in thermoplastic polyurethane. With increase of CNT, electrical conductivity, strength, and elastic modulus increased, As increase in elastic modulus improves the printing capability as they increase resistance to buckling. These are the three graphs which are showing the improvement in tensile strength, flexural strength, and the electrical conductivity of the material with the increase in CNT content. Next category is the nanocomposites consisting of graphene. Dewey et al. Carried their work where they mixed graphene nanoplatelets in the ABS. 4% by weight of
Abhishek, hello.
Yes, sir.
Is it possible to conclude now?
Yes, sir. So these are the conclusions that are drawn from my study. So necessarily loading of filler material after a certain limit gives detrimental effect on the workability. Hence limitation of upper loading ratio is imposed. And the homogeneous diffusion of filler material inside the base thermoplastic matrix reduce the agglomerates and void contribute maximum in improving properties in composites. Inclusion of filler material improves targeted material properties, but sometimes it gives an adverse effect on the properties like break elongation. So, but this can be overcome by adding one or more filler and can reduce this adverse effect. But not much literature is available for such systems. To make the use of additive manufacturing in practical application, parts of improved material properties are required. And nanocomposites will play a crucial role in developing materials which can fulfill the demands of the future. So these are the references that are taken out in this work. Thank you.
Thank you, sir. The session has been given queries to the chair.
I would open it to the participants for sharing because this has been a review paper. And how is the validation that you are trying to do here, Abhishek? Any points on validation, how you do this?
Ma'am, this is basically only the review work, and ma'am, in future I'm planning to carry out, make some composites.
You're planning to do it experimental?
Yes, ma'am.
Okay,
I have also decided some of the mixers that can be useful in developing nanocomposites.
Okay, good. Thank you. All the best.
Okay, thank you, ma'am.
Thank you once again. Are there any further queries? There are no further queries. So moving on to the next presentation, we have Yan from Swinburne University of Technology, Malaysia, going to present on his paper entitled Flutter Analysis of Wind Turbine Blade with Carbon Nanotube Reinforced Vinyl Ester. So please.
Yeah. Can you hear me?
Yes, I can hear you.
Oh, yeah, okay. Can you access my screen now?
Yes, your screen is visible.
Visible, okay, fine. Okay, so I'm back again, Saravana Kannan. This is another paper from our team. I'm presenting on behalf of our team. This is flutter analysis of wind turbine blade. So in our previous research paper, the aeroelastic behavior, aeroelastic instability, we discussed about different angle for different design blade, swept blade. Here, flutter analysis. Flutter actually, of course, it is the vibration. A flutter analysis of the wind turbine blade with the carbon nanotube reinforced vinyl ester, alternative new material for the blade, wind turbine blade. Of course, to reduce the deflection, reduce the instability, and get the better power production. Okay, so what do you mean by the flutter? Again, this is the aeroelastic instability which causes the large amplitude of vibration of the structure. So the blades vibrate. Normally, structure to vibrate, they may result in structural failure. Okay, so especially when the vibration reaches the maximum beyond the structure natural frequency, because every structure they have some allowable frequency within this range. When it is rotate, definitely it is vibrate. But it is crossing the natural limit. What happened? Definitely make failure. Current wind turbine blades are made up of carbon. Most of the wind turbine blades are made up of glass fiber reinforced with the polyester or carbon fiber and epoxy resins. Okay, so we are looking for the new blade material, that is a carbon nanotube process, mechanical carbon nanotube. They actually have a mechanical properties that can fulfill the requirement of the modern large-scale wind turbine blades, such as low weight, high strength, and high stiffness, and finally a long fatigue life. Okay, this is the purpose of finding the alternative material to reduce the instability. Okay, so aim of this research, different operating speed, we 8 to 24 meter per second taken for the analysis, and different pitch angle. So previous one, yaw angle, but here we taken for the new material. This is the yaw angle. This is the yaw angle for the previous aeroelastic instability for the swept blade. Here we taken for the different pitch angle, for corresponding different pitch angle with the different speed, how actually the pressure distribution in the blade behaves, and how actually the deflection of the blade happens for the new material compared with the current material, carbon fiber. Okay, so that is of the interest for this research. So changing the material of the wind turbine blade, new material, adapting the material, suitable material, that is the CNT, carbon nanotube vinyl ester composite with the triaxial fiber, both comparing with the current material. So these are the data collected from the new material, material properties and thickness, and reinforced polyester material, and for the carbon fiber and carbon nanotube. And the methodology for this research, starting with the CFD, creating the mesh, creating the model, meshing, and select suitable turbulent model, applying the boundary condition, and run the CFD simulation of the wind turbine blade, obtaining the aerodynamic load and the pressure distribution on the blade for the different velocities. And that pressure distribution data given to the CFD and the FEA combined fluid structure interaction result, that is the FEA model, and applying the boundary condition and run the FEA simulation to get the obtain the results to compare for the flutter speed, deflection, and the stress. That is the procedure or the flow of this research. And this is the 3D model wind turbine blade taken from the NREL laboratory, the wind turbine wind pack 1.5 megawatt with the aerofoil design and designed in the SolidWorks surface loafing. And for the computational domain for this research to analyze the aeroelastic behavior, the flutter analysis, cost of vibration analysis, and meshing these details. And these are the computational simulation. Definitely, ANSYS Fluent we taken, and turbulent flow model, viscous K omega SST taken for that, and boundary condition including the rotational velocity, checking the calculation to improve the meshing for 1,400 iteration, because we use the academic version only for this research. This is our undergraduate research project, student project. And finite element analysis model taken for the aerodynamic loading with the fluent comparison, and the centrifugal loading, gravitational force. Those are the information taken for the FEA analysis, and FEA for the multi-layer material and thickness deflection data taken from the literature for the corresponding material, CNT, and the triaxial fibers, including the natural, the glass fiber taken for that. And these are the results for the pressure distribution from the ANSYS Fluent. So when we look at for the different velocity, different speed, 8 meter per second, 12 meter per second, up to 24 meter per second. For various speed, we taken the pressure curve for the blade for the different material. So pressure contours, so taken for this analysis. So based on the one, we compare the results for the pressure distribution for the previous research with the current one, previous with the different material with the current one. So the pressure distribution over for the different one is, for the current one is lower than compared to the previous material, the current material taken for analysis, comparing with our CNT. That is, percentage difference between the previous research, that is 40%, 44%, pressure difference low. So definitely if the pressure difference low over the blade, which caused the deflection, definitely lower deflection, we can predict. So these are the deflection over for the blade taken for the FEA analysis. For the 8 meter per second and 24 meter per second for the FEA analysis given in the meter. These values are. So the deflection for the blade, mainly the deflection mostly in the tip of the blade, we can notice. Okay, this is the comparison for the deflection. When we comparing with the CNT, the carbon nanotube, this is the carbon nanotube. So this one very, 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 very low comparing with the previous research done for the carbon fiber, a glass fiber material. Okay, so that is the percentage of the deflection reduction. It is a 56.46%. We managed to reduce the deflection over the blade. If you're replacing the new material with the blade for the CNT material. So this is the validation we did for 2 different model, testing the vibration, frequency data. That is for model 1 and model 2, the percentage difference between the experimental data, because we compared our experimental data with the one with our material, our research, CNT research. This is the CNT one, and comparing with the experimental research. So the results are more close to this. But anyway, the experimental data and the simulation data is not close because of the different adaptation, accuracy for the meshing, and the data taken for the analysis and validation, everything. But it's close to the frequency because the level range is 4 to 5. The frequency ranges for the vibration is very close. So we definitely can justify that our validation, accurate. For the model 1, 6.28. For the model 2, that validation is very huge, 36.53%. And this is the conclusion for this research, including future work. The largest deflection of the wind turbine blade at 8 meter per second. So the deflection is very high at 8 meter per second, and largest the total deflection for the CNT, carbon nanotube vinyl ester composite, our new material adapt for the wind turbine blade, which is 0.6539 meter, and for the triaxial fiber is 0.6205, comparing to the carbon fiber material. So better significant results we obtained. That means the deflection is very lower, and the improvement what we need to do, deeper study in the material property of the wind turbine composite layers, because we did not focus on the different layer by layer. So this is our future research. We are working for the layer by layer analysis for identifying the accuracy for the deflection. And we need to, the compare diagram for comparison for the natural frequency. So we still need to compare our frequency data with the natural frequency rate, because as I told you in the beginning, every structures, they have some natural frequency. If the frequency, when it is oscillate, when the natural frequency level, the oscillation frequency level beyond the natural frequency level, definitely this will fail. So that comparison, we're still looking for that. And that's it.
Thank you, sir. The session has been queried to the chair.
Yeah.
So I think this is a combination of the work that you're trying to do, sir, on the wind turbine, right? With the 2 papers that you're presented.
Yes, ma'am.
And sir, the carbon nanotubes have been in existence in practice, no? So how different is the work that you're trying to bring out?
The carbon nanotube, when you look at the title, carbon nanotube is combining with the another material,
So
carbon
actually, you're looking at the reinforced, carbon nanotube material, right? That's what you're trying to bring out. Yeah. Okay. I got it. Okay. Thank you, sir.
Reinforced with multiple material we can do, because one part reinforced. Yeah.
Right.
Vinyl ester. Yeah, I forgot the name.
Yeah. Actually, sir, are you planning to manufacture, or you're just planning to do the theoretical analysis side?
Actually, most of the analysis what we are doing is the simulation only. Now we are going for the numerical because of the budget and the research money.
Yeah.
Not go for the experimental.
Funding is a struggle. Yeah, I understand. Yes. Okay.
This one only the fluid dynamics investigations only. Yeah, but
anyway,
because it's not 100%. Yeah.
Anyway, nice efforts to see you work on latest areas. Okay, the session is open for audience to have any discussion if required.
No queries, ma'am. We can move forward to the next session.
Please go ahead.
Thank you for your wonderful presentation, sir. Moving on to the next presentation, we have Bibin K. Tarian from National Institute of Technology, Calicut, going to present his paper entitled on enhanced of material removal rate in electrical discharge machining of in Cornell 718 using Cairo treated graphite electrodes. So please.
Good evening, everyone. I hope it's visible.
Yes, yes, please go ahead.
Okay, good evening, everyone. Myself, Bibin Gatharian. This is called from National Institute of Technology, Calicut. So I'm here to present my findings on the topic enhancement of material removal rate in electrical discharge machining of Inconel 718 using cryo-treated graphite electrodes. So these are the contents of the presentation. Let me move on to the introduction. So we have seen an uprising in the trend, the usage of nickel-based alloys, based superalloys in the aerospace, chemical and marine industries because of its superior mechanical properties at elevated temperatures. So at the same time, there is a requirement for new processes which could machine these materials, because in the conventional machining process, it would be very hard to machine this kind of materials. So in this work, we were using EDM. So am I audible?
Yes, yes.
Okay. So this is the illustration of EDM. So as you can see, there are two electrodes. One is a tool and the other one is a workpiece, which have the opposite polarity. And there will be a discharge spark in between these electrodes, which causes the material to melt and evaporate. So the basic mechanism behind the EDM is spark erosion technique. But there are some limitations in this process, like the lower value of material removal rate, then higher surface roughness, and the tool wear. So as an improvisation, we have been employing this cryogenic treatment. So what cryogenics is like that, we are dipping a material in liquid nitrogen for a certain period below the room temperature. There are two types in the type of cryogenic treatment. One is a shallow and other one is a deep, depending upon the temperature that we are employing and the soaking time. So in the traditional machining processes, the studies in cryogenics have resulted in improvisation. Actually, cryogenic treatment in a material alters the conductivity, both the thermal and electrical conductivity. So these are the literatures in the area of cryogenic machining in EDM. So from this, we can conclude that the studies resulted in improvisation of the EDM material removal rate, then surface roughness and the surface quality. At the same time, tool wear also. So our objective is to explore the effects of cryogenic treatment on material removal rate using cryo-treated graphite electrodes. This is actually a preliminary experiment in our research. So let me go to the experimental details. So here our workpiece is Inconel. The EDM machine is and all the further details are given below. The tool is graphite electrode having 10 mm dia. That is one is the normal and second one is the cryo-treated electrode. The input parameters that we have considered is the current, pulse on time, and the pulse of time. Current is the maximum current in the circuit that we have been using. Pulse on time is the time for which the pulse is on for the material removal, and the pulse of time is the time elapsed between two pulses. Here the output parameter, as I have already said, is the material removal rate. And in our case, we have treated the electrode cryogenically at minus 190 degrees Celsius, 96 degrees Celsius in liquid nitrogen for a soak time of 24 hours. This is Synchronous 718. Then the chemical composition is given below. It has been employed at high temperature applications, as I have already explained. So these are the factors and their corresponding levels are given. As based on our preliminary experiments, we have conducted 9 experiments based on L9 orthogonal array. Not a higher number of run, I know, but still as a preliminary experiment, we have done this. So this is the EDM specimen. And these are the experiment results. We have been done for the non-cryogenic treated electrode and the cryo-treated electrode. So let me go to the effect of the parameters. So we have considered 3 parameters, that is current, pulse on time, and the pulse of time. And their effect to the MRR is given here. As the current increases, that is the peak current in the circuit increases, The melting and the vaporization also increases. That improves the MRR. But in case of T-on, it shows a reverse trend. It can be due to the ineffective flushing or the recast layer. So the rate is decreased, and that yet to be discovered from more number of experiments in the next trial. And the T-off is also having a slight increase when in comparison with the MRR. This is the EDM surfaces. This image has been taken using Brooker Alicona Infinite Focus. So here I have given the lowest MRR and the highest MRR. As we can see, the highest MRR corresponding to SA value of 7.297. Here SA is the aerial surface roughness. That means in case of EDM-like surfaces, the conventional RA value is not that much suitable. So we are here finding out the SA, which is the aerial one. So it shows the higher value of SA. That means deeper craters are formed. Then this is the diagrammatic representation of the same. Then the effector parameters using the cryo-treated electrode. Their trends were the same as in the non-cryo-treated, but we have seen an improvisation in the value of MRR. As highest MRR is found to be 8.108, not the MRR, which is the SA value, which is 8.108, and the highest MRR is found for the same experiment. So, concluding my results, here higher values of current will improve MRR as per our observation, and there is a slight change in the value of T-on, slight reverse in the trend of T-on that could be explored by further experiments. And the highest MRR is found across the setting, current 8 ampere, pulse on time 25 microseconds, pulse of time 8 microseconds, and an average improvement of 21.39% is found in MRR of graphite electrodes when they are cryogenically treated. This shows an increase in MRR by using cryogen treated treatment, and this laid us the foundation for the next work, which is focusing on the surface morphological analysis and the modified surfaces. And these are the reference. I would like to acknowledge the DST lab in NIT Calicut and the ISRO sponsored lab in Amaljodi College of Engineering and the Mac tools for machining works. Thank you.
Okay, nice observations, Bipin. Good experiments. I think you have a little more longer way to complete the experiments to get into the real judgment. So, nice to see the good work being happening. Okay.
Thank you, ma'am.
The floor is open for questions for the participants.
Bipin.
Yes, sir.
As you're working on Inconel 718, right?
Yeah, we have done the preliminary experiments now in Inconel 718. I'm not actually working on the Inconel one.
You didn't actual experiment you didn't done with 718.
No. This experiments I have run with 718. My actual research work is on one novel material.
Oh, novel material. Okay, fine. So, what is the metallographical changes that occurring on the surface of 718 while cryo treatments?
Sir, actually, we are treating the electrode, not on the material.
Yeah, fine.
So, while treating the electrode, the observations I have seen and from the literature I have observed is that the conductivity changes, so the electrode were decreased.
Okay.
So it improves the dimensional accuracy of the final product or the whole that we were intended to manufacture. And the metallographical changes that we need to explore further.
Okay. Fine. So actually, you have done 718 with graphite electrode, right?
Yes, sir.
Okay. So did you check the surface roughness afterwards?
Yeah. We have checked the surface roughness as the aerial surface roughness, not the RA value.
Okay, not the RA value, right? Yeah, fine. Okay. So that was my intent, because the surface is super layer, right? So you have a multiple metallographic structure there, because it consists of a lot more alloying elements, which is present inside the surface also. So already the surface is tough.
Yes.
So what find the difficulties while doing machining?
The difficulties were the debris formation was very frequent.
Okay.
We were doing several multiple runs to find out the range of parameters.
Fine.
Then like the carbon deposits, that's a usual thing, I know, but still the debris and carbon deposits were the struggle.
Okay, and mostly the cyanonate, in which area it's used for, whether for nuclear sector or power plant sector?
Sir, I have chosen the aeronautical application in which every industry where high temperature applications, it's widely used.
Okay, fine. Yeah, thank you. Good work.
Thank you, sir.
Thank you for your wonderful presentation, sir. Moving on to the next presentation, we have Anida Zaid from National Institute of Technology, Warangal, going to give a presentation on paper entitled Finite Element Modeling of Non-Isothermal Curing Kinetics for Resin Transfer Modeling Process. Please.
Yes, good afternoon to all. Is my screen visible?
Your screen is not visible yet.
Okay, just a minute. Yes, is it visible now? I'm audible?
Yes, ma'am.
Visible.
Good afternoon to all. This is Anita Zhade, research scholar at Department of Chemical Engineering, NIT Warangal. Today I'm going to present on finite element modeling of non-isothermal curing kinetics for RTM process. So coming to the introduction of RTM process, there are major 4 stages. First, we have to cut the fiber preform into the desired shape and then load to the mold, that is called the preform loading. Then we have to inject the pressurized resin through the appropriate injection port till the fiber preform gets completely saturated with resin. That is called the mold filling stage. After that, the curing step begins where the heat transfer occurs from the mold wall to the saturated preform. Here, a number of cross-linking reactions also occur and phase change also occurs. After this curing step, we'll remove the mold, we'll remove the composite part from the mold, that is called the demolding. So we are majorly focusing on the curing stage for the non-isothermal thermal profile in this work. There are a number of applications for this RTM process like car structures, aeroplane structures, and rocketry applications. Coming to the mathematical modeling, so in this work we have used COMSOL multiphysics as a software and 2 physics heat transfer in solids and domain ODEs and DEs. So in the heat transfer in solids, we have incorporated the heat, transient energy balance equation at the curing stage. So this is transient temperature term, conduction term, and heat source term. So under this heat source term, we have combined the other physics, domain ODEs and DEs with this algebraic equation. So this algebraic equation dou alpha by dou t is called the cure rate model, which is a function of temperature and the degree of cure alpha.
Anita, sorry to interrupt you. I think your slides are not changing. You please continue with your present slide wherever you want presenting. I think 3rd or 4th slide you're in.
Is it changing now?
Not yet.
You haven't shared the slideshow.
Yeah, I will stop sharing and again I will share once. Okay.
Yes.
Is it changing now? Not it?
Yeah, now it's changing.
Okay. Sorry for the interruption. So I was at 3rd slide. So for the initial condition, for this model, we have used time t is equal to 0, initial temperature T0, and the degree of cure will be 0. And the boundary conditions are the mold wall temperature, which is specified to perform the curing reaction. So a number of empirical models has been used to perform this curing simulation, which is nth order model, Kamala-Sorer's model, and there are a number of modified forms where this nth order model is k into 1 minus alpha to the power of n. This k is a rate constant which is represented in terms of Arrhenius law. N is order of reaction. So for this study, we have used, these are the raw material parameters and kinetic parameters we have used for this study. Coming to the simulation part, so we have used, initially we have simulated 2D geometry.
Anika, still your slides are not getting changed.
Okay. Is it changing now like this?
It is changing, but why you are not in slideshow mode?
Actually, once I come to the slideshow mode, I think slides are not visible. So I will, is it okay if I will present like this now?
Yeah, that is okay, but it is better to go from the top, like you just from the third slide, whatever modeling slides are there, you go from there.
Okay, okay. Okay, sir. Okay. So this is a modeling part. So two models I have used: physics, heat transfer in solids, and domain ODEs. This is a transient energy balance equation, and in this cure rate models, function of temperature and degree of cure. The initial conditions T0, degree of cure equal to 0, and boundary condition temperature T is equal to T mole, which is a mole temperature. So these are the number of cure rate models, empirical models that we have used for this study, different Neanderthal model and Cumberland-Soren model. These are the raw material parameters which is used. So here K is a rate constant, which is in terms of Arrhenius law, and F of alpha is a degree of cure, that is N is order of reaction. So coming to the numerical simulation part, so here we have used 2D geometry initially with dimensions 0.2 meter by 1 meter, and we have selected 3 points A, B, C in such a way that so that we can study the temperature dependency on degree of cure along the composite plate. We have also performed the grid independent study with respect to mesh sizing. So we have changed the domain elements from 86 to around 3150, but we did not observe a significant variation in degree of cure with respect to mesh sizing. So for this study, we have used free triangular mesh with 476 domain elements. So coming to the results part, initially we have done the isothermal study for different temperatures, temperature ranging from 320 Kelvin to 400 Kelvin with a difference of 320 Kelvin. So here if you'll see with increasing temperature, the time to complete the cure reaction has been reduced. So for the non-isothermal transient study, we have used initial temperature as 315 Kelvin and mole temperature as 380 Kelvin. So this figure B and figure C are the transient variation of degree of cure and temperature with respect to time along the different locations, point A, B, and C. So if you'll see, as we move from the mold boundary to the center of the composite plate, the time to complete the cure reaction has been increased. So this red line is point C, which is close to the mold wall, and the blue line point A, which is away from the mold wall. Then these are the surface plots. Actually, this is GIF, as I have not given the slideshow mode, so it's not visible here. But this surface plot will change with respect to time. So as the temperature gradient will reduce, definitely the degree of cure reaction has been started completing. So because of, so I'm not able to see this now. Now transient variation of degree of cure for different empirical models. So different, like these are the two rate constant models, Cumberland-Soren model form 1, 2, and 3. So for these two rate constant model, there are significant variation in degree of cure among the different points, whereas for the one rate constant model, has same trend in the degree of cure for different points, although the point which is close to the mold wall has taken less time to reach to complete the cure reaction compared to the other points. Now coming to the 3D geometry to study the efficacy of the COMSOL multiphysics simulator, we have considered 3D geometry on curved composite plate, and here we have varied the thickness from 10 mm, 20 mm to 30 mm. We have analyzed the effect of degree of cure and temperature at particular point, that is point D, which is specified here in this geometry. So if you see, with increasing thickness, definitely obviously the time to complete the cure reaction will also increase. And this we can see from the degree of cure as well as the transient variation temperature plot. These are the surface plots also. GIF actually this moves with time, but I will again reduce the slideshow mode because these are surface plot. We should show that the degree of cure is changing with respect to time, and there is significant difference in reaching the cure state for the different thicknesses. Coming to the conclusion, so we have developed the COMSOL multiphysics simulator for non-isothermal curing simulation. We have also observed the transient variation of temperature and degree of cure for 2D and 3D composite structure. So from this, we have observed that with increasing temperature, the time to complete the cure reaction has been reduced, and to complete the cure reaction has been increased with increasing the thickness of the 3D composite plate. These are the references, and thank you.
Thank you. The session has been given.
Audience, may I please take up?
Session is open for queries. Those who have queries, you can ask her. Anita ma'am.
Yes, sir.
Have you done any experimental work?
Not yet, sir. We are working on simulation part and optimization part till now.
Okay, fine.
Are there any queries left? Okay, I guess there are not. So moving on to the next presentation, we have Mohammed Sanoof S. from NSS College Engineering, Palakkad, going to give a presentation on his paper entitled Parametric Optimization of Hole Geometry in Laser Drilled in Cornell 825 by Gray-Based Response Surface Methodology. So please. So you're inaudible, sir.
Yes, you're audible. Mohammed Sanoof, you are inaudible.
Hello?
Yes, you're audible now.
Here I'm presenting parametric optimization of hole geometry in laser drilled in Cornell 825 plate by Gray-based response surface methodology. Here we run a micro drilling process. Micro drilling is a process of making hole in the range of 1 micrometer to 1 mm. And there are a lot of methods, conventional and non-conventional methods. But in conventional methods, the tool breakage is high than tool wear. So in drilling advanced engineering material, non-conventional method like laser, EDM, ECM, and electron beam, spark-assisted chemical engraving, etc. are used. But compared to other non-conventional method, laser is a non-contact and material independent, low-cost and fast method, which is most favorable in industry. And the most common laser used for micro drilling process is Nd:YAG laser. First, it can produce a concentrated beam. And the performance parameters in micro hole drilling, laser drilling is the quality characteristic, material removal rate, surface roughness, and the geometrical characteristic, hole taper, and hole circularity and hole overcut.
Mohammed, can you move to your current slide? Sorry to disturb you.
Hey, ma'am. metallurgical characteristic, heat affected zone, recast layer, and spatter formation micrometers. And I'm studying the geometrical characteristic of the hole.
Sanuf,
That is,
Sanuf,
yes, sir.
your slide is not changing.
Okay.
Can you kindly move on to slideshow?
Sir, I'm in slideshow mode.
No, you
Sir,
haven't presented in slideshow.
No, sometimes I think Google recently has some issues. So if they are, if they have opted for screen share, it might come. But in some cases, this issues there. So you can actually select your current slide. That will be the easiest way right now to save time.
Sir, can you see?
And, yeah, now it is visible. Yes.
And we work on superalloy laser drilling in superalloy. Superalloy is a material which possesses high mechanical strength and surface integrity at a high temperature. It in the applications aircraft, gas turbine, steam turbine, power plant, petrochemical industries, etc. And we selected the material Inconel 825, then a nickel-based superalloy which is high resistant to corrosion at a high temperature. It critical application include acid production, oil and gas piping, chemical processing, pickling equipments, etc. In many Inconel 825, that is due to its poor thermal conductivity, high toughness, work hardening behavior of this alloy cause high heat generation in cutting zone, which the conventional method drilling is not possible. And abrasive carbide particles adhere to the tool surface, causes reduced surface finish in this machining of Inconel 825. Here the outline of our work is effect of laser power process parameters such as air pressure, trepanning, speed, frequency and lamp current on the output response of hole circularity at entry and hole taper is studied by gray-based response surface methodology. An experimental material of 10 by 10 2 mm thickness and Taguchi L18 orthogonal array is used for experimentation. 3 levels of parameters are used in the these parameters are in the working range and the output response are taken as hole taper and hole circularity at entry. It's a geometrical characteristic and the hole taper is calculated by this equation and hole circularity by diameter. Hole circularity is the roundness of the hole. It is measured by the equation minimum diameter at entrance and divided by maximum diameter at entrance. The gray-based response surface methodology. The gray relation analysis is a gray relation analysis and impact measuring method in gray system theory that analyzes uncertain relation between one main factor and another factor in the given system. Here, our input parameters are first normalized in gray relation analysis. This method converts multiple response into a single response. To the single response called overall gray relation coefficient. The overall performance characteristic of multiple response was depends upon the calculated gray relation analysis, gray relational grade, and the response surface methodology. The response surface methodology is a dynamic tool which uses to relate the process parameter to response obtained to maximization or minimization of the quality characteristic. Complexity of the experiment increases with the number of response observed in the experiment. That is, the response surface methodology is used to form a mathematical relation between the input parameter and the output, and by maximizing, applying generally second order polynomial equation is used as a to relate, and maximizing or minimizing the relation can give the optimal combination. Then the gray-based response methodology benefit is when combining gray relation analysis with response surface methodology. If you only use hello, if you only use response surface methodology, there are lot of equation can be formed by different output. But when we use gray relation analysis with response surface methodology, we combine the outputs into one output, so the equation can be reduced to one. These are the experiment results obtained, and gray relation grade of the output response is calculated. From this result, the experiment run 5 has the maximum gray relational grade. That is, it is the most optimal combination parameter. that is it gets the rank 1. These are the microscopic image of the hole drilled at entry and exit. The mean effect plot of GRG is plotted. The air pressure is increasing, then it is decreasing. In lamp current, it is decreasing, then it is increasing. The response table for the signal to noise ratio is plotted. To know the significance of the significance or contribution of the each parameter on the output, that is, air pressure has the rank 1 and lamp current has 2. Trepanic speed is 3 and frequency is 4. That means the air pressure is the more contribute to the increase in the grade relational grade. That is
Sanup, conclude your presentation.
These are the interaction plots plotted using grade relational grade. Interactive effects of grade with each input parameter is plotted, and we'll conclude that maximum grade relation grade is obtained at the parametric combination of air pressure 5 bar, trepanic speed 75 millimeter per second, and frequency 4 kilohertz, and lamp current of 18 ampere. Air pressure and lamp current is the significant parameter controlling the hole circularity and hole taper. High frequency and trepanic speed reduces the GRG grade because it reduces the interaction time to melt and vaporize the metal. And lower and higher value of lamp current gives the increase in GRG, but higher value of lamp current gives higher value of GRG due to effective melting and vaporization of metal.
Thank you. The session has been given. Queries to the chair.
Okay, quickly, Mohammed, can you tell us what are the outcomes in 1 or 2 points? Can you tell us the what is this? Where is this going to be applied, and what is the outcome of this work?
Here we done a project that is to find the optimal combination of parameter to drill Inconel 825 alloy.
Okay, fine.
That is the highest GRG grade means it is the optimal combination that give better result.
Okay.
I think that makes it clear, no? Yeah, okay. Shall we call the next presenter, or is there any audience questions to be addressed?
No, ma'am. We can move forward.
Okay, thank you for your presentation, Sanup. So, moving on to the next presentation, we have Makesh Kumar M from KBR Institute of Engineering and Technology, Coimbatore, going to give a presentation and on his paper entitled on microstructural and mechanical properties, evaluation of dissimilar aluminum alloy and bronze joints using friction stir welding. So please.
Yeah, thank you, sir. Yeah, thank you, sir. Myself, I am Sasikumar, working as an assistant professor in the Department of Aeronautical Engineering from Karananiri Institute of Technology, Coimbatore. I am going to present a paper on microstructural and mechanical properties evaluation of dissimilar aluminum alloys and bronze joints using frictional stir welding. Please, the slide is changing.
Yes, it is.
Yeah, thank you, sir. Yeah, thank you, sir. So the main objective of our paper is to identify the functional behavior of an frictional stir weldings of aluminum and as well as of bronze by the metrology study and mechanical testing, and to evaluate the influence of the process parameters of FSW, that is fusion stir weldings on the weld mix, and to reveal the microstructural characterization and mechanical behavior of dissimilar weld joints of aluminum and bronze materials. So here we have chosen aluminum and bronze materials and dissimilar metals. From the literature review studies, this is the minimum papers we got. So we have chosen as an aluminum and as well as of bronze material. So then now we are going to see about the introduction. So introduction about FSW, that is frictional stir welding, is a kind of new solid state welding process which is versatile and energy efficient and environmental friendly process. And the frictional stir welding was invented at the welding institutions of the United Kingdom in 1991. These frictional stir welding techniques use a non-consumable rotating tool for the metal joining process. The tool is made with a special designed pin and shoulder with many be inserted on the bending edges of plate and has to be jointed and transferred along the line of the joint. So based on the research works, so we have investigated for various purposes like marine and aerospace application and automobile application and chemicals and as well as of nuclear industries. They have used these type of techniques. So based on the literature study, the research has been carried out for dissimilar metals like aluminum and bronze. And we have carried out also microstructure and mechanical behavior studies we have carried out, and we have done investigation. So frictional stir welding, it's an cylindrical and shoulder tool with a profiled pin is rotated and slowly plugged into the joint line between two pieces and welded together. This frictional heat is generated between the wear resisting welding tool and the material of the workpiece. The heat causes the material to soften without reaching the melting point. That will called as an glass transient temperature, and it allows two transfers of the tool along the weld line. So it leaves a solid phase between the two dissimilar metals. So these are the methodologies we have followed. First, we have done a literature review, and we have identified the problem identification, and we have came out with the objectives and process parameters, and we have selected the rotational speed, welding speed, and as an axial load, and we have compared the two. We have taken the two result. One is tensile strength, and second thing is microscopic test. And finally, we have plotted the result and the discussion. So this is the experimental of our works. So here we have shown the two different metals. One is aluminum, and second thing is bronze, and we have done an FSW process here. The dimensions were given here, 100 into 50, and the thickness is 4 mm. So this is the machine which we have used for welding, frictional stir welding. And this is the diagram which indicates how the process has been taken out during the process. So these are the two base materials, that is one is bronze, then second thing is aluminum. So here the base metal as aluminum and bronze. The tool material here we have used is H13 tool steel. So this is what about the chemical composition of aluminum plate and as well as of bronze, like magnesium this much of percentage, and ferrous and copper, tin, zinc, magnesium, silicons, carbon, titanium, aluminum, and as well as of bronze materials. So these are the percentages of chemical composition. So this is the plate dimensions. The both plates are in same dimensions, like aluminum and bronze are in 100 into 50 and 100 into 50, and thickness also we have maintained of 4. But here we have kept a constant rotating speed as 1125 RPM from the literature review. The same thing we have taken, and we have compared the result also, and we have kept a traveling speed in a line. So 50 for 15 we have taken on 20 and 25 mm per minute, and the axial force on 100 kilonewton in the downward directions. So this is the tool material composition, like H13 tool steels, carbon, magnesium, copper, magnesium, molybdenum, phosphorus, silicon, sulfur, vanadium. So this much of percentage also available for H13. So this is the welding parameter. These are the three comparative studies we have done for specimen 1, specimen 2, specimen 3 at constant rotating speed, and welding speed varies like 15, 20, and 25. And the axial forces are 10 kilonewton, 10 kilonewton, 10 kilonewton, and tool tight angle is 2 degree. So this is a tool profile. So pin profile is a conical pin, and we have used of 20 mm radius of the tool. So this is the sample of welding done for sample 1, sample 2, and sample 3. So from the test we have taken the tensile strength. So the welding speed is 15, 20, and 25. So from the study, the 20 gives the better result. 20 for a load which we acts of 2 kilonewton, and the elongation has been happened for 15.6, and the yield strength is 79.4 megapascal, and tensile strength is 94.5. So when compared to sample 1 and sample 3, sample 2 is the best result we have got in a tensile strength.
Sorry for interrupting. Kindly come to the conclusion and the results.
From the conclusion, we came to know that so we have done an frictional stir welding for two compound. One is aluminum and second thing is bronze together, and finally we came to have a result that the second one, that is for the constant RPM 1000 125 rpm for 20 mm per minute has got the best mechanical properties as a tensile strength of 87%. And the same thing we have done, the elongation was also good, and the microbiology microstructures of boundary layer has given off a good result in the for the sample 2. And the hardness also we have taken, and the hardness for the second component was sample was very good. So these are the reference which we have taken, and thank you. These are the problems which we have identified while we are doing of experimental methods. Thank you, sir.
Thank you. The session has been given. Queries to the chair.
It's a really good work with a lot of good outcomes and solutions. Nice to see good work happening. So, you had any industrial collaboration here, or?
No, ma'am. No, we done by ourselves. This tool has been available in KPN Institute of Technology. That is
Okay.
frictional welding they have, ma'am.
Okay, good. Any questions from the participants?
Yes. Sai? Shashi?
Yes, sir.
Kumar, yes. What is the temperature that developed at the Najit area?
At that welding point.
Yes, welding point.
Around, I think 500 degrees Celsius around.
Whether you have measured?
No, sir, we have not measured that temperature, but we have taken that base metal and heat affected zone. We have calculated. Still, it is in a processor. Only few data we have taken.
Okay. Whether you have provided any rake angle for doing FSW?
So, no, sir. What you have asked again?
Whether you have provided any rake angle to the tool while doing FSW process?
No, sir. No, sir.
And not giving it a rake angle?
No, sir. It indicates of 2 degrees, sir. 2 degree we have given off.
2 degree. Then
Yes,
how
sir.
do you optimize the pros parameters?
We have kept as an 2 degree for that particular one.
Before welding, whether you have optimized your pros parameters?
No, sir. No, we have taken.
So you directly selected one parameter. With that parameter, you weld all the plates.
Yes, sir. Just we have taken as a sample one and we have done it.
So whether you have you got a defect-free weldment?
No, sir. We got some defects also, which I have not indicated here.
Okay, so with that defect plate, you have done the mechanical test.
Yes, sir. With that small, yes, sir. Still, it is in process. So whatever the thing we have taken that I have presented here.
Okay, so before proceeding, you need to optimize the pros parameter to obtain a good weldment. Then you need to characterize metallurgical as well as mechanically.
Okay, sir. Okay, sir. Okay.
Yeah, fine. Yeah, thank you.
Thank you.
Thank you for your wonderful presentation, Sasi Kumar.
Thank you, sir.
Well, moving on to the next presentation, we have Ivan Jones from St. Joseph's College Engineering and Technology, Pale, going to give a presentation on his paper entitled "Effect of Discharge Gap of EDM Using Dischargeability Function Analysis." So, please.
Okay, sir. Thank you. Sir, the screen is visible or not, sir? Is it okay now?
Your presentation is, yeah, it's visible right now.
Okay, thank you. Myself, Ivan Jones, and I'm a research scholar in the Department of Mechanical Engineering, St. Joseph College of Engineering, Pale. My topic is effect of discharge gap on EDM using dischargeability function analysis. So, as a part of this introduction, this is introduction about the EDM. In the recent years, the trend of miniaturization of the products is persistent in the areas. So, in the areas of biotechnology, environmental, and medical industries, and the demand for the micro products and the components has been rapidly increasing in various industries. So, mediums has been developed as a precise machining process to produce accurate features in electrically conducting materials. So objective of the current work is to find out the optimal gap distance which has to be maintained constant during the EDM machining process. So and also machining in micro. Okay, the optimized values of the optimized values of the input parameters will be found out with the help of desirable function analysis. So to find out the optimal gap that its optimization is done with desirable function analysis. So moving into my experimental setup in our lab, this is a helium setup, and it is fabricated here only. And you can see that the helium setup is there, the oscilloscope, the function generator, and also the DC supply, some electronic components and all are there. So this is the focused view of that particular work chamber. You can see that the linear actuator, tool holder, and the workpieces are there. So in that experience setup for the EDM consisting of the function generator, tool holder, DC supply, and the tank with electrolyte. So this is a methodology. The three input parameters are voltage, frequency, and the duty factor. The three levels are given to the voltage: 35 volt, 40, and 45 volts. With the frequency selected with 2 kilohertz, 3 kilohertz, and 4 kilohertz, and also the duty factor 60%, 70%, 80%. The output parameters we have measured is a material mode, tool wear rate, and the overcut. So our aim is to improve the material removal rate and also to reduce tool wear rate and radial overcut. So the workpiece used is a copper plate of 0.6 mm thickness, and also the tool electrode is a copper tungsten electrode, and a total of 27 experiments are to be carried out with manual feeding mechanism, and the process parameter optimization carried out with desirability function analysis with various steps. In the desirability function analysis, basically there are three response characteristics: nominal the best, larger the better, and the smaller the better. But in this study, larger the better for the material removal rate, and also the smaller the better the case for the tool wear rate and the radial overcut. So these are our objectives. With this tool, desirability function analysis, our aim is to larger the better for the material removal and tool wear rate, and the radial overcut is for smaller the better. Then here in this desirability function, individual desirability indexes are to be find out. In that step, there are some steps are involved in the desirability function analysis. First of all, individual desirability values has to be find out for each case or for each input parameter, and after that, a composite desirability function, composite desirability value has to be found out by combining all the individual desirability values. Then individual desirability evaluates how the setting optimizes a single response. The composite desirability evaluates how the setting optimizes for the set of responses overall. So these are the fundamental elements in the desirability function analysis: individual desirability values and also the composite desirability values. These are to be find out in that process. The desirability has a range 0 to 1. If it is the 1, that represents the ideal case, and for the 0, then the more of the responses are outside the acceptable limit. So the obtained desirable values are between the 0 and 1. In cases that value is 0, or in some cases it could be 1. Higher the composite desirable value implies better product quality. Therefore, on the basis of composite desirability, the parameter effect of optimal level for each control parameter are estimated. So with that composite desirable value, parameter effect of each of this value, and also to optimize that value. The most significant parameters out of the from the desirability analysis, we have a set of values, and that set which one is having the most effective influence on that desired output. That are find out with the help of ANOVA method. The percentage contribution is calculated, and the accurate distribution can be determined by ANOVA. The ANOVA is done with Minitab 17 software. The ANOVA is calculated by giving the input parameters as voltage, frequency, and duty factor, the three input parameters, and also the output as the composite desirability obtained from result function analysis. These are the input and output values for that ANOVA. Then the results experiments were conducted based on Taguchi Elson orthogon array. The material removal rate and the tool wear rate were measured with the electronic weighing method, and also radial output is measured with optical microscope, that is tool makers microscope, and optical method is there for that measurement of radial overcut. And these are the input parameters for that orthogonal. Voltage ranges from 35, 40, and 45. That the frequency values are 2 kilohertz, 4 kilohertz, and 6 kilohertz. The duty factor are 60, 70, and 80%, and also the gap distance selected as 0.5, 1, and 1.5 mm. So that obtained a material removal rate, tool well rate, and the radial overcuts are listed here. These are the input table. In the desirability function analysis, signal to noise ratio for MRR is calculated based on larger the best option, and also for tool wear rate and radial overcut it is calculated based on smaller the better option. And that table is given below from the Minita. So signal to noise ratio for MRR, signal tool wear rate and radial overcut is listed here for the order design combinations of the input parameters. Based on the desirable function analysis, optimization, and also the optimization steps, the evaluate individual desirability and composite desirability for each of the experiments using also ortho array is given in table. Okay, the higher composite desirability value represents that corresponding exponent results is closer to the ideally normalized value. So, in that this is that individual values of the desirability function and also the composite values. You can see A, B, C, D are the three input parameter values, and it is only from 1 to 15 only. The remaining is there on the next slide. And also we can see the material removal, tool wear rate, and radial overcut. The corresponding individual desirability values are there. So in that calculations, so there are some equations are there that is not included in this presentation. That after the calculation process and those steps, we are arrived at this values between that ranges from 0 to 1. For initial cases, we can see 0.5 and 5. So the values are there, and that extreme right we can see the composite desirability values that represents all the three out parameter combinations. So that represents the composite desirability value. With that, we can arrive at one conclusion. So this is the remaining combinations of the input parameters and the corresponding desirability composite desirability values. So next is to with the help of ANOVA. The purpose of the ANOVA is to investigate which machining parameters significantly affect the optimum output. So in that optimum output, which one is significantly affects. So which parameters?
Sir, sorry for interrupting as we are exceeding time limit. Can you conclude your presentation if possible?
Okay, sir. Okay.
Yeah, fine. Thank you.
So my conclusion is that the optimal level of parameters obtained in the case of different gap distances have checked, and the best results will get at 0.5 mm gap distance. The results of ANOVA indicate that all factors have almost equal contribution towards affecting the multiple optimization process. Here we have multi-objective optimization process. So each are having significant influence. Out of which, according to DF optimization method, the optimal settings for the machining parameters are identified as voltage of 39.95 volt, frequency as 4.67 kilohertz, and duty factor as 67.47%, and the gap distance is 0.5 mm respectively. From DFA, it is found that optimal results is obtained in the intermediate voltage, frequency, and duty factor, and that gap obtained as 0.5 mm gap distance. So these are the references for this particular work. Thank you. Thank you.
Okay, thank you for your presentation. The session has been given queries to the chair.
Okay, I win. For implementation, what do you think are the different considerations that you need to take to this experiment model that you have shown?
Madam, I'm not hearing clearly, madam. Can you repeat it again?
For the implementation of, say, the four variables that you have shown, the voltage, frequency, and the gap and the distance. So what are the different, parameters that you need to look at, or what are the different steps that you need to look?
Which is the optimum values, optimum combination value for that given input parameter value that I have to you have to optimize that with the DF analysis. And for the implementation part means which one is the optimal result? Is that you mean or?
No, what are the different concerns that you will have while implementing these parameters? Because though theoretically we are saying these are the the optimum values. When you look into the implementation side, there will be more factors that you need to consider. And there is one more question that I would like to know, and why you have opted for ANOVA?
For that ANOVA case, which input parameters having significantly contribute to that optimum value that we
No,
have?
there are other statistical methods. No, why you have opted for ANOVA is my question. Design of experiments, have you tried?
No, design of experiments not tried actually. ANOVA is just taking ANOVA. That's all. There is no other. Because I think it is it gives more better results. Also, I'm also a co-guide for that, and there is one more guide, and we combinedly decided to go for this, and that's what.
Okay, over to the participants.
Hello, Evan.
Yes, hello, sir.
Yeah, my name is Bibin. I'm from NIT Calicut. So, your experimental perspective on the discharge gap is quite impressive. I would like to know more like that. How the discharge gap going to affect the performance or the machinability of the process? I just want to know. Like, I hope you will be considering the parameters like surface quality for sure.
Okay.
So what were your expectations? Have you done it, or are you going to perform this kind of experiments?
And it is actually done one of my students here, and he passed out now. And I was one of the co-guide for that particular research work. And input parameters, experimental means that gap we manually give that feed, and we check what are the results obtained by setting three gap values of 0.5, 1 and 1.5, and that's all. We just as a part of the experiment part only, we have changed that gap distance as set three different values.
No, actually, I am asking like that. I was just curious about the further work in your study. Like, in the sense, are you going for the surface quality kind of things?
Yes, actually, surface quality thing, as we have only just material removal and tool wear rate. We only inspected, and the surface quality thing currently we have not done anything about that. But also, we have to check for by after checking the radial overcut, and only radial overcut you have inspected. No any other surface quality you haven't, but taken any steps to measure that. Currently,
okay.
Nothing is done, but anyway, in the future studies or future works, we are focusing on that.
Okay, and one more thing, the experimental setup you have just shown is quite impressive. I think it's not the ready-made one. You have built this one.
No, it is not a ready-made one. Actually, we have in our lab we have fabricated it. It's our limited resources, and it is not any. It is just fabricated in our lab.
Okay, that's quite impressive. Thank you, Evan. That's all.
Okay, thank you, thank you.
Any queries?
No queries. So the session is going to an end. The contributory oral presentation of the afternoon section is going to wind up now. So thank you, Dr. Nidhi MP, Chair of the afternoon session track 1, Associate Professor MBCET, and Co-Chair Dr. Adishir, Associate Professor FISAT, for the giving a constructive ideas and constructive suggestions to the participants. And we have witnessed a very good exploration of research works. So thank you all for being with us and giving patience for listening to our each presentation, even though we have exceeded more time. So thank you to our students coordinator, Ivan, Yazin, Gokul, and Gautami for conducting a smooth conduct of the oral contributory presentations. So once again, I'm thanking everyone for participating to our conference ISMAT 2021. So we will resume to our second day session by tomorrow 9 a.m. Thank you.
Thank you. And